About 700 million years after the universe began, astronomers identified an extremely massive black hole weighing approximately 50 million times the mass of the Sun. It was not located within a galaxy, nor was it associated with any nearby cluster of stars, and current theories do not predict such an object could form in these conditions. The James Webb Space Telescope detected this black hole, which exists in a region of the early universe where a black hole of this size should not exist. So how does the universe work? What is the nature of stars and gravity? Before we begin this cosmic journey, comment below where in the world you're watching from and what the time is there now. We're always excited about hearing where our viewers are from. A black hole is one of the most mysterious and powerful objects in the entire universe. It is a region in space where matter has been compressed so tightly that it becomes unimaginably dense. This incredible density gives it an extraordinarily strong gravitational pull, so strong that nothing, not even light, can escape once it crosses a certain invisible boundary. This is why it is called a black hole. Anything that passes this boundary disappears forever, leaving no trace behind. The concept of a black hole comes from Albert Einstein's groundbreaking theory of general relativity. According to his theory, if a huge amount of mass is packed into a small enough space, it can warp both space and time to such an extreme that a black hole forms. The outer edge of a black hole, where escape becomes impossible, is known as the event horizon. Once anything crosses this line, even light, it cannot return. Despite their immense power, black holes do not look remarkable from the outside. If you were floating nearby, you would see no bumps, marks, or clues revealing the extraordinary object within. Einstein's theory predicts that you would not even notice crossing the event horizon, at least not immediately. In some ways, black holes behave like a perfect black body in physics. They do not reflect any light, they simply absorb everything around them, but quantum physics adds an even stranger twist. In the 1970s, scientist Stephen Hawking used quantum field theory to show that black holes are not entirely black. They emit a tiny amount of heat, now called Hawking radiation, from the edge of the event horizon. However, this radiation is extremely faint. For black holes formed from stars, the heat is only a few billionths of a Kelvin, far too small to detect with current technology. The idea of objects so massive that light could not escape them was first considered in the 18th century by John Michel, an English clergyman and astronomer, and independently by Pierre-Simon Laplace, a French mathematician and physicist. Michel in the year 1784 wrote a letter calculating that a star with the same density as the Sun, but 500 times larger in radius, would have gravity so strong that light could not escape. Laplace later discussed similar dark stars in his book Exposition du Système du Monde, published in 1796, and even provided mathematical explanations in a journal. At first, these ideas fascinated scientists, but interest faded in the early 19th century when people realized that light behaves as a wave, raising doubts about whether gravity could trap it. The modern understanding of black holes began in 1915, when Albert Einstein introduced general relativity, proving that gravity can indeed influence light. Just a few months later, German physicist Karl Schwarzschild found a solution to Einstein's equations that described how gravity behaves around a massive spherical object. This solution revealed a mysterious boundary, now known as the Schwarzschild radius, where space and time behave in extreme ways. Around the same time, Johannes Droste, a student of Hendrik Lorentz, independently derived a similar solution and provided additional details. Scientists at the time did not fully understand the implications of this boundary, but it was clear that something extraordinary was happening. It was not until 1958 that David Finkelstein explained that a black hole is a region from which nothing can escape, not even light. For many years, black holes were considered purely theoretical, mathematical curiosities rather than real objects in the universe. But during the 1960s, scientists began to realize that black holes were a natural outcome of Einstein's theory, not just imaginary constructs. The first black hole identified with confidence was Cygnus X1, discovered in 1970 by several teams of researchers. Black holes usually form when massive stars much larger than our Sun reach the end of their lives and collapse under their own gravity. Once formed, they can grow by pulling in gas, dust, and even other stars from their surroundings. When a black hole reaches the mass of millions of suns, it becomes a supermassive black hole. These giants can grow further by merging with other black holes or by swallowing massive clouds of gas at once. Scientists now believe that most galaxies, including the Milky Way, harbour a supermassive black hole at their centre. Although we cannot see black holes directly, we can detect them by observing their effects on nearby matter. When gas and dust fall toward a black hole, they form a spinning disk called an accretion disk. Friction in this disk makes it extremely hot and bright, producing light across many wavelengths. In some extreme cases, this process creates a quasar, an object so luminous that it can outshine an entire galaxy. If a star ventures too close to a supermassive black hole, it can be stretched and torn apart by the black hole's gravity. This process, known as spaghettification, transforms the star into long streams of hot gas that glow brightly before disappearing into the black hole. Astronomers can also study the movements of stars orbiting a black hole to determine its mass and location. This method has helped identify many black hole candidates, particularly in binary systems, where one star orbits an invisible companion likely to be a black hole. One of the most famous black holes discovered this way is at the centre of our galaxy, called Sagittarius A star. By observing the motions of stars near it, scientists estimate that it has about 4,300,000 times the mass of our Sun. In 1924, British astronomer Arthur Eddington showed that this strange behaviour at the Schwarzschild radius wasn't a real physical problem. It was more of an issue with the way the math was written. Later, in 1933, Georges Lemaitre proved that this problem was only a coordinate issue, not something that actually existed in nature. In a book published in 1926, Eddington imagined what would happen if a real star had so much mass that it shrank to its Schwarzschild radius. He said that a star that heavy would trap light, bend space so much it would fold in on itself, and shift its light so far into the red part of the spectrum that it would disappear completely. Then came another important step. In 1931, a young Indian physicist named Subrahmanyan Chandrasekhar used the ideas of special relativity to calculate how much mass a white dwarf star could have before it became unstable. He found that if the mass went above about 1.4 times the mass of the Sun, the star would no longer be able to hold itself up. This limit later became known as the Chandrasekhar limit. Many scientists at the time didn't believe him. Eddington and others thought there must be some unknown force that would stop a star from collapsing completely. In a way, they were partly right. Stars just a little heavier than that limit can collapse into neutron stars, which are extremely dense but still stable. But in 1939, American scientists Robert Oppenheimer and George Volkoff pushed the idea further. They suggested that if a neutron star was too heavy, even that wouldn't be enough to stop it from collapsing. They introduced the Tolman-Oppenheimer-Volkoff limit, which they estimated at around 0.7 times the Sun's mass, based on early calculations. Later studies that included the effects of the strong nuclear force revised the estimate to between 1.5 and 3 times the Sun's mass. In recent years, especially after the observation of a neutron star collision in the event called JWST 170817, scientists narrowed the limit even further, estimating it to be about 2.17 times the mass of the Sun. Oppenheimer and his team also had a strange idea about what happens at the Schwarzschild radius. They thought that to an outside observer, time would seem to stop at the edge of the black hole. They called these objects frozen stars because anyone watching from far away would see the star frozen in time as it collapsed. Also in 1939, Einstein himself published a paper trying to argue that black holes could not form. But just a few months later, Oppenheimer and his student Hartland Snyder published another paper called On Continued Gravitational Contraction, using Einstein's own theory to show how a black hole could actually form from a collapsing star. Their model became the first serious scientific prediction of black holes in modern physics. In 1958, physicist David Finkelstein finally described the Schwarzschild radius as an event horizon, a point of no return, where anything that crosses it can never come back. He explained it as a one-way barrier. Things could go in, but nothing, not even information, could come out. Finkelstein also created a new way of looking at space and time that made it easier to understand what happens from the viewpoint of someone falling into a black hole. Around the same time, mathematician Martin Kruskal developed similar ideas, but they weren't fully understood at first. Eventually, the combined work of Kruskal and George Sekaras led to the creation of new mathematical coordinates, Kruskal-Sekaras coordinates, that helped scientists describe black holes from both inside and outside perspectives. The period between the mid-1960s and the mid-1970s is often called the golden age of black hole research. During these 10 exciting years, black holes and Einstein's theory of general relativity went from being fringe ideas to becoming a major focus of mainstream science. During this time, scientists made several important discoveries about black holes. In the year 1963, a mathematician named Roy Kerr found an exact solution to Einstein's equations that described a black hole that spins. This was a major step forward because most real black holes in space are expected to rotate. 2 years later, in 1965, another scientist named Ezra Newman found a solution for a black hole that not only spins, but also has an electric charge. As scientists studied more, a powerful idea began to take shape, known as the no-hair theorem. This idea was developed thanks to the work of physicists Werner Israel, Brandon Carter, and David Robinson. It said that if a black hole stops changing, in other words becomes stable, it can be completely described by just 3 things: its mass, how fast it spins, called angular momentum, and its electric charge. According to this idea, black holes are very simple on the outside, no extra features or hair needed. At first, some scientists thought these strange black hole features, like their incredible density or the existence of a central singularity, were just tricks caused by oversimplified equations. In particular, 3 Russian scientists, Vladimir Belinsky, Isaac Kalatnikov, and Evgeny Lifshitz, believed that real black holes wouldn't have these singularities in most cases. They even tried to prove this with math. But in the late 1960s, 2 brilliant scientists, Roger Penrose and Stephen Hawking, used new math techniques to prove the opposite. Singularities do appear in many real situations, not just rare or idealized ones. This was a turning point in physics. In recognition of this work, Roger Penrose was awarded half of the Nobel Prize in Physics in the year 2020. Unfortunately, Stephen Hawking died in the year 2018, so he could not get the prize. During this same golden age, astronomers were also making exciting discoveries. In the year 1967, scientists Anthony Hewish and Jocelyn Bell Burnell found mysterious, fast-pulsing signals from space. These were soon identified as pulsars, or quickly spinning neutron stars. By 1969, it was clear that these were real objects in space, not just ideas. This discovery showed that extremely dense stars, like neutron stars and black holes, were real, encouraging scientists to take these complex objects much more seriously. Another major discovery came from observations in Greenwich and Toronto in the early 1970s. Scientists studied a mysterious X-ray source called Cygnus X1, which had first been seen in 1964. After years of study, Cygnus X1 became the first object in the universe that was widely accepted to be a real black hole. At the same time, in the early 1970s, researchers such as James Bardeen, Jacob Bekenstein, Brandon Carter, and Stephen Hawking started a new field called black hole thermodynamics. This area looked at black holes in a new way, by comparing them to everyday physics, like the laws of heat and energy. They found deep links. A black hole's mass is like energy, its surface area is like disorder, entropy, and its surface gravity is like temperature. Then, in the year 1974, Stephen Hawking went further. Using the rules of quantum physics, he showed that black holes aren't completely black. They actually give off a faint glow of energy, now called Hawking radiation. This discovery shocked the world because it meant that black holes can slowly disappear over time. More recently, on the 11th of February 2016, the LIGO and Virgo collaborations announced something historic. For the first time ever, they had directly detected gravitational waves, tiny ripples in space and time caused by 2 black holes merging. This discovery confirmed an important prediction of Einstein's theory and opened a whole new way of studying the universe. Then, on the 10th of April, 2019, another amazing milestone happened. Scientists shared the first ever image of a black hole, taken by the Event Horizon Telescope in 2017. This image showed the glowing edge of the giant black hole at the centre of the galaxy Messier 87, more than 50 million light-years away. More discoveries are still happening. Observations from the Gaia space mission revealed a black hole called Gaia BH1, which is about 1,560 light-years away from Earth. This black hole seems to have a sun-like star orbiting it. Another black hole, Gaia BH2, may have a brown dwarf orbiting it. Even though we've only found a few dozen black holes in our Milky Way galaxy, Scientists think there could be hundreds of millions more. Most of them are probably quiet and alone, not pulling in matter or giving off light. These hidden black holes could only be found by their gravity. By how they bend light from distant stars, a phenomenon called gravitational lensing. Scientists use a more precise way to describe a black hole. They say it's any object whose mass is packed into a space smaller than its Schwarzschild radius, a special size limit predicted by the math of Albert Einstein's general theory of relativity. This means if something is heavy enough and small enough, it becomes a black hole. Once a black hole has formed and settled into a steady state, scientists believe it can be completely described by just three features: its mass, how much matter it has, its electric charge, and how fast it spins, called angular momentum. This idea is known as the no-hair theorem. It means black holes are simple in a way. They don't have other features or hair that make them different. So if two black holes have the same mass, charge, and spin, they're completely identical. They can't be told apart no matter what created them or what fell into them. However, scientists still don't know if this is completely true in the real world, since it's a big mystery that modern physics hasn't fully solved yet. What makes these three properties special is that they can be detected from outside the black hole. For example, if a black hole is electrically charged, it can push away or pull in other charged objects, just like any other charged object in space. Similarly, scientists can measure the total mass of a black hole from far away by using gravity-based methods, such as something called ADM mass. The spin of the black hole can also be detected from a distance by watching how it twists nearby space and time, a strange effect predicted by general relativity, known as the Lenz-Thirring effect. But here's something unusual. When something falls into a black hole, all details about that object, its shape, its structure, where its electric charges are, get spread out evenly over the surface of the black hole's boundary, called the event horizon. All that information is lost to the outside world. It's as if the black hole erases the details. Scientists compare the behavior of this surface to a stretchy sheet with electrical resistance and friction, kind of like rubber that also conducts electricity. This idea is called the membrane paradigm. It's very different from how normal forces like magnetism or light work, because those forces don't have friction and don't forget information. But black holes do, which leads to one of the biggest puzzles in physics, the black hole information loss paradox. This paradox is about how black holes forget things. Once a black hole reaches its stable state, with just mass, charge, and spin, it no longer shows any sign of what it swallowed. That includes tiny details that can't be measured from far away, like how many protons or electrons went into it. These are things known as quantum numbers, and normally they're kept in physical processes. But black holes seem to break that rule, and scientists still don't know why. The simplest kind of black hole only has mass. It doesn't have any charge or spin. These are called Schwarzschild black holes, named after the German physicist Karl Schwarzschild, who found the mathematical solution in the year 1916. According to a rule called Birkhoff's theorem, these black holes are perfectly round, and are the only ones that behave like this in empty space. In fact, from far away, their gravity is no different from the gravity of any other round object of the same mass. So the popular idea that black holes suck in everything is only true when you get close to them. From a distance, they behave just like stars or planets of the same weight. There are more complex kinds of black holes too. If a black hole doesn't spin but has an electric charge, it's described by what's called the Reissner-Nordström metric. If it spins but has no charge, it follows the Kerr metric. And if it has both spin and charge, it's described by the most complete solution we know so far, called the Kerr-Newman metric. Now, while a black hole's mass can be any positive number, the charge and spin can't be just anything, they're limited by the mass. If a black hole has the maximum allowed amount of charge or spin for its mass, it's called extremal. There are some strange theoretical solutions to Einstein's equations where a black hole goes beyond this limit, but those don't have an event horizon. They show their central singularity to the universe, which scientists call a naked singularity. This is considered impossible in reality, according to something called the cosmic censorship hypothesis. This idea says the universe hides all singularities behind event horizons, and computer models and simulations seem to support this. Because the force of electricity is so much stronger than gravity, stars that collapse into black holes are expected to stay almost neutral. They don't keep much electric charge. But rotation is another matter. Most compact cosmic objects like neutron stars and black holes are expected to spin. For example, there's a black hole candidate called GRS 1915+105. It's part of a binary X-ray system and appears to spin very, very fast, close to the maximum speed allowed. Black holes are usually sorted based on their mass, no matter how fast they spin. The size of a black hole is directly linked to its mass. This size is measured by the radius of its event horizon, the Schwarzschild radius. The most important feature of a black hole is this event horizon. It's a one-way boundary in space. Once something passes through it, it can never come back, not even light. That's why we say black holes trap everything. If something happens inside the event horizon, no signal from that event can reach the outside world. From our point of view, it's as if the event never happened. Einstein's theory of general relativity also says that anything with mass bends the fabric of space and time. The more mass something has, the more it warps this fabric. Near a black hole, the warping becomes extreme. At the event horizon, the warping is so strong that nothing, not even light, can escape. Here's an interesting thought experiment. Suppose an observer is floating far away from a black hole, watching a clock near the event horizon. That clock would seem to tick slower and slower as it gets closer to the black hole. This strange effect is called gravitational time dilation. If something falls toward the black hole, it appears to move slower and slower, as if it's frozen in time at the edge. From far away, it would look like the object takes forever to fall in. Also, the light coming from the object would get stretched out and dim, becoming redder and harder to see. Eventually, it would fade completely. This might sound like a slow process, but in most cases, the object disappears from sight in less than 1 second. But here's the twist. If someone could fall into a black hole without being destroyed, a purely imaginary scenario, they wouldn't notice anything strange when they cross the event horizon. Their own clocks would tick normally, and they wouldn't feel anything unusual at that exact point. This is because, in Einstein's theory, you can't tell when you cross the horizon just by using local measurements. This idea comes from what's known as the equivalence principle. However, the shape of the event horizon is always round when a black hole is not spinning. If it does spin, the shape gets slightly squashed, wider around the middle and flatter at the poles like a spinning planet. But no matter what, the horizon always forms a closed surface around the black hole. At the very centre of a black hole, according to the basic and idealised Schwarzschild model, is something incredibly strange and mysterious, a gravitational singularity. This is a region where space and time become so warped and twisted by gravity that their usual rules completely break down. In this place, the bending of space-time becomes infinite, meaning it bends beyond any imaginable limit. If the black hole is not spinning, then the singularity is squeezed into a single point with no width, no depth, and no height. Literally zero volume. But if the black hole is rotating, then this central singularity stretches into a thin ring-shaped structure that lies flat, spinning in the same direction as the black hole itself. Despite having zero volume, this strange region holds all the mass of the black hole. That means it has infinite density, an unimaginable amount of matter packed into a space so small that it can't even be measured. Now, the Schwarzschild model, which describes a non-spinning, uncharged black hole, is not accurate when it comes to what exactly happens right at the singularity. But one thing is clear: anyone who falls into a Schwarzschild black hole and crosses the event horizon, the invisible boundary around the black hole, has no way to escape. No amount of effort or rocket power can save them. They can slow down their fall for a while by firing rockets in the opposite direction, but they can't stop the inevitable. As they get closer to the centre, they would experience a strange and terrifying process called spaghettification, or sometimes jokingly the noodle effect. This happens because the gravitational pull at their feet would be far stronger than at their head, or vice versa, stretching their body into a long, thin string. Eventually they would be crushed into the singularity, their mass becoming part of the black hole. Not all black holes are simple, smooth objects. Some are much stranger. If a black hole is spinning, scientists call it a Kerr black hole. If it carries an electric charge, it is called a Reissner-Nordström black hole. In these cases, the behaviour of the black hole becomes far more unusual. Some scientific theories even suggest that it might be possible to avoid the singularity, the infinitely dense point at the centre, entirely. In theory, if you follow the mathematics to its extreme, You could pass through such a black hole and emerge somewhere else. This could mean arriving in a completely different part of space, or perhaps even another universe. In this scenario, the black hole acts like a kind of tunnel, often called a wormhole. But there is a major problem. Even the smallest disturbance, a single particle falling in, would destroy this delicate structure. For now, this idea remains purely theoretical, a fascinating thought experiment rather than a real possibility. Some mathematical models of spinning black holes go even further. They allow for what are called closed time-like curves. In theory, these curves could let an object travel back in time. But this leads to serious puzzles, such as the famous grandfather paradox. What would happen if you went back in time and accidentally prevented your own birth? Most scientists think that once we have a complete theory that combines the rules of quantum mechanics with Einstein's general relativity, these strange effects will not actually happen. Singularities themselves are a clear sign that general relativity, Einstein's theory of gravity, is no longer enough. When matter is compressed to extreme densities, the laws of quantum physics must also be considered. Yet so far, no one has successfully combined gravity and quantum mechanics into one unified theory. Scientists continue to work on this challenge, aiming to create a theory of quantum gravity. Such a theory could explain black holes in a way that removes the strange and unsettling idea of singularities. Moving outward from the center, black holes have other fascinating regions. One of these is the photon sphere, a spherical zone just outside the event horizon, where light itself can orbit the black hole. For a black hole that is not spinning, this zone is located at a distance equal to 1.5 times the Schwarzschild radius, which is the size of the event horizon. Within the photon sphere, photons, particles of light, can circle the black hole. However, this orbit is extremely unstable. Even a tiny disturbance, such as another particle or a small nudge, can knock the photon out of orbit. It may spiral inward, falling into the black hole, or it may be flung outward, escaping into space. Any light we observe from near the photon sphere must originate from just outside this zone, because anything crossing that boundary cannot return. If the black hole is spinning, the situation becomes more complex. The size and shape of the photon sphere change depending on how fast the black hole spins and in which direction the light orbits. Light can circle in the same direction as the spin, called prograde, or in the opposite direction, called retrograde, which affects how close the light can safely orbit. Spinning black holes also have a remarkable region known as the ergosphere. This area lies just outside the event horizon, where the very fabric of space and time is dragged along by the black hole's rotation. This strange effect, predicted by general relativity, is called frame dragging. Inside the ergosphere, it is impossible to stand still. Everything is forced to move in the direction of the black hole's spin. To remain stationary, an object would have to travel faster than light in the opposite direction, which is impossible. The ergosphere touches the event horizon at the poles but stretches much farther out around the equator. Despite this, objects can still escape from the ergosphere. In fact, there is a way to harness the black hole's rotation to gain energy, called the Penrose process. If an object is thrown into the ergosphere in the right way, it can split into two pieces. One falls into the black hole, while the other escapes with more energy than it had before. The extra energy comes from the black hole's spin, which gradually slows down as this process continues. An even stronger effect, called the Blandford-Znajek process, occurs when powerful magnetic fields are involved. This mechanism may explain the enormous jets of energy and particles that shoot from the centers of galaxies, known as quasars and active galactic nuclei. Another key concept in black hole physics is the innermost stable circular orbit, or ISCO. In normal gravity, like Newtonian gravity, objects can orbit around another object at almost any distance. But near a black hole, there is a limit. If an object moves too close, its circular orbit becomes unstable. A small inward step from this boundary will send it spiraling into the black hole with no chance of escape. How close this orbit can be depends on the black hole's spin. The faster it spins, the closer an object can orbit safely. However, there is the plunging region. Once something enters this zone, escape is impossible. The object will fall directly toward the black hole at nearly the speed of light. This is a one-way trip with no return, marking the ultimate boundary of the black hole's influence. Black holes are some of the strangest and most extreme objects in the universe, so much so that for many years, scientists questioned whether they could actually exist in reality. or if they were just unusual solutions produced by Albert Einstein's mathematical equations. Even Einstein himself was skeptical. He believed that when a star collapsed under its own weight, the spinning motion of its particles, what scientists call angular momentum, would prevent it from collapsing completely, keeping it stable at a certain size. To grow that big, a black hole would need to spin in the same direction as the material falling into it all the time. But in reality, matter in space often falls in from random directions. This randomness, called chaotic accretion, means that black holes often get pushed in both directions, sometimes spinning faster and sometimes slowing down. Over time, these changes usually slow the black hole's spin more than they speed it up. There's more. Black holes also grow by merging with other black holes, but mergers too usually end up lowering the total spin. All of these effects together make it very rare for a black hole to grow beyond about 50 billion times the mass of the Sun, especially if it doesn't spin very fast. Only in rare cosmic situations do black holes even come close to that huge size. Even though today's ultramassive black holes, called UMBHs, found in quasars and at the centres of galaxies can't grow bigger than about 5 to 27 billion times the mass of our Sun, at least not through their surrounding disks of falling matter, and especially not given the current age of the universe. Some scientists think these cosmic giants might still grow far in the future. In fact, in the very distant future, during the slow collapse of huge groups of galaxies called superclusters, some of these black holes could reach almost unbelievably huge sizes, up to 100 trillion times the mass of the Sun. These enormous black holes have a powerful effect in the universe. The strong gravity at the centre of many galaxies, where supermassive black holes sit, is thought to drive some of the most energetic objects in space, like Seyfert galaxies and quasars. Interestingly, the size of a black hole at a galaxy's centre often matches the size and mass of the galaxy itself, but this connection changes depending on the kind of galaxy. There's even a special link called the M-sigma relation, which connects a black hole's mass to how fast the stars in the galaxy's central bulge are moving. Faster star motion usually means a heavier black hole. When scientists talk about an AGN, or active galactic nucleus, they mean a galaxy centre that has a supermassive black hole actively pulling in matter. This process gives off a lot of light, making the core very bright. Our own Milky Way's centre, however, isn't quite bright enough to be called an AGN. To explain the many types of AGNs, astronomers came up with a unified model. This model says that the differences we see mostly come from a few things, like how bright the AGN is and what angle we view the black holes surrounding matter from. There are two main types of AGNs. One type mainly shines from a thick disk of matter, falling into the black hole, while the other shoots out strong jets of energy, moving near the speed of light from the black hole's poles. When two galaxies, each with a supermassive black hole, collide and merge, the black holes don't just stay put. Because of something called dynamical friction, these black holes slowly move toward the centre of the new galaxy. Eventually they get close enough, less than 1,000 parsecs apart, to form a pair. As they keep interacting with the surrounding stars and gas, they spiral even closer, becoming a tightly bound binary system with a gap of just 10 parsecs or less. If they get within just 1,000th of a parsec of each other, the energy released as gravitational waves will finally merge them into one single, massive black hole. After this dramatic collision, the galaxy formed from the merger will have already settled, and any early star-forming fireworks or AGN activity will have faded. But the black hole merger leaves behind something else, a strong blast of gravitational waves. These waves can give the resulting black hole a huge push, sending it through space at thousands of kilometers per second. In some cases, the push is strong enough to kick the black hole out of the galaxy. This strange event is called a gravitational recoil. There's another way a black hole can be thrown out of a galaxy. Imagine two galaxies merging, forming a pair of black holes. Then a third galaxy joins, adding another black hole to the center. When three black holes interact, things can get messy. Usually the lightest of the three is flung into space, while the other two move in the opposite direction as a new pair. This kind of three-body gravitational dance is called a slingshot recoil. Any of the three black holes can end up being ejected, and those thrown into space are called runaway black holes. Astronomers have found several clues that might point to such recoiling black holes. For example, if a bright AGN or quasar isn't in the middle of a galaxy where it should be, that could be a sign. Or, if we see two different light signals from one quasar, it might hint that a black hole is being flung away. Some possible examples of recoiling black holes are in galaxies like NGC 3718, SDSS 1133, 3C186, E1821+643, and SDSS-J 0927+2943. Potential runaway black holes might include HE 0450-2958, CID42, and objects near the dwarf galaxy RCP-28. Runaway black holes can leave a trail of star formation as they move. In fact, a straight line of new stars near RCP-28 was once thought to be the wake left by a runaway black hole. But later, research suggested it might just be a small galaxy seen from the side without a central bulge. There's also a fascinating process called Hawking radiation, named after physicist Stephen Hawking. According to quantum theory, black holes aren't completely black. They slowly give off tiny amounts of heat energy because of strange effects near their edges, called event horizons. This process slowly shrinks the black hole, and if left alone for long enough, it would eventually disappear completely. For example, a black hole 100 billion times heavier than the Sun would take about 2.1 times 10 to the power of 100 years to vanish. A much bigger black hole, formed during the collapse of a supercluster in the far future, with a mass of 100 trillion suns, could take about 2.1 times 10 to the power of 1009 years to fully disappear. Some of the strongest clues that black holes exist come from a phenomenon called the Doppler effect. This is the same effect that changes a siren's sound as it moves past you. In space, it affects light. When matter is moving away, its light looks redder, red-shifted. When matter is moving toward us, its light looks bluer, blue-shifted. Near a black hole, things get extreme. Matter orbiting close must move incredibly fast, almost as fast as light. Because of this, the part moving away looks much fainter, while the part moving toward us looks brighter. This makes something that is actually evenly shaped, like a ring or disk, look uneven and distorted. Modern computer images of black holes take this effect into account. One famous example shows what the black hole at the center of the Milky Way, called Sagittarius A star, might look like. This is based on a scientific model that many experts think is very accurate. However, our current telescopes still aren't sharp enough to see this directly, so we rely on simulations for now. Still, scientists have observed matter swirling farther out from suspected black holes. This matter moves much slower than light, making it easier to measure. For example, water molecules in space can give off specific radio signals called masers, similar to lasers but with microwaves instead of light. By studying these masers in nearby galaxies, scientists have seen very fast Keplerian motion, meaning the matter moves as Kepler's laws predict. This only happens when an enormous amount of mass is packed into a small area, something only black holes, or nearly formed black holes, can explain. For more distant galaxies, astronomers can study the width of certain light signals, called broad spectral lines, which gives clues about gas orbiting near the black hole's event horizon, the point of no return. One advanced method, called reverberation mapping, looks at how these signals change over time to estimate the black hole's mass and possibly how fast it spins. There is strong evidence that the Milky Way has a supermassive black hole at its center, about 26,000 light-years from the solar system. This region is called Sagittarius A star. Scientists have studied a star called S2, which moves in a stretched oval orbit around this mysterious object. It takes about 15 years and 2 months for S2 to complete one full orbit, and it gets as close as 17 light-hours, about 120 times the distance between the Earth and the Sun, to the black hole's center. From how S2 moves, scientists have guessed that the central object must have a mass of about 4 million times the mass of our Sun, yet it must fit into a space no larger than 17 light-hours across, otherwise S2 would crash into it. Another star, S14, has helped show that this strange object is even smaller, with a radius of less than 6 1/4 light-hours, about the size of Uranus's orbit around the Sun. No other known object in the universe, except a black hole, could be this heavy and compact. Even more amazing are the infrared observations of bright flares coming from Sagittarius A star. These show a kind of glowing plasma, hot charged gas, orbiting very fast, about 30% the speed of light, in tight circles just outside the black hole's point of no return. These flares seem to come from a superheated hot spot on the accretion disk, the spinning disk of matter falling into the black hole. This hotspot seems to follow a circular path within a strong magnetic field. On January 5, 2015, NASA observed an X-ray flare from Sagittarius A star that was 400 times brighter than usual, a record-breaking event. Scientists think this might have been caused either by an asteroid being torn apart as it fell into the black hole, or by magnetic fields twisting and snapping inside the swirling gas. So far, we have solid proof of supermassive black holes in only a few galaxies. These include our Milky Way, the Andromeda Galaxy, also called M31, a smaller nearby galaxy called M32, and a few others outside our local group like NGC 4395. In these galaxies, the speeds of stars or gas near the centre rise sharply as you move closer inward, which matches what you'd expect if a massive object, a black hole, was pulling them in. In most other galaxies we've looked at, these speeds don't rise the same way, so we can't say for sure whether a black hole is there or not. Still, most astronomers think that nearly every galaxy has a supermassive black hole at its centre. This idea comes from something called the M-sigma relation. In simple terms, this means there is a strong link between the mass of a galaxy's central black hole and how fast the stars in the galaxy's bulge are moving around. This pattern has been seen in about 10 galaxies, where we have very accurate measurements, and it suggests that galaxies and their black holes might grow and change together. On March 28, 2011, astronomers saw something incredible: a supermassive black hole tearing a mid-sized star apart. They saw a sudden burst of X-rays and other signals, and the only explanation that fits is that a star got too close and was torn apart by the black hole's gravity. This happened in a galaxy where the central black hole had been quiet until then. Based on what was seen, scientists think the black hole had a mass of around 1 million times that of the Sun. The event also created powerful jets of material shooting out at high speeds, almost as fast as light, something called a relativistic outflow. A large part of the star likely fell into the black hole, and future observations will help confirm this idea by studying how the light fades over time. The Andromeda Galaxy, which is about 2.5 million light-years from Earth, contains a central black hole about 140 million times the mass of the Sun, much bigger than the one in the Milky Way. An even larger black hole lives in the giant galaxy Messier 87, located around 48 million light-years away. This black hole is about 6.5 billion solar masses. The largest known black hole in our nearby space is found in the NGC 4889 galaxy, in the Coma Berenices constellation. It is around 336 million light-years from Earth, and contains a black hole with a mass estimated at 21 billion times the Sun's mass. When it comes to quasars, extremely bright and distant objects powered by black holes, we use indirect ways to guess their black hole masses. These methods are tricky and have a lot of uncertainty. One extreme example is the quasar TON 618, which may contain a black hole with a mass of about 40.7 billion times that of the Sun. Its light comes from a time when the universe was still young, with a redshift of 2.219. Other quasars with large black holes include APM 08279 plus 5255, with about 10 billion solar masses, and SMSS J2157 28.21-3602151, with about 34 billion solar masses, almost 10,000 times bigger than the Milky Way's central black hole. Some galaxies seem to have two supermassive black holes at their centres, forming a pair. If these black holes were to collide, the event would create strong gravitational waves. This kind of double system of supermassive black holes is thought to be a common result of galaxies merging. One well-known example is the binary pair in the galaxy OJ 287, which is located 3.5 billion light-years away. This pair contains the most massive black hole ever discovered in such a system, with a mass estimated at 18 billion times the mass of the Sun. In 2011, a supermassive black hole was found in the small galaxy Henneis 210, which does not have a bulge. The exact meaning of this discovery for how black holes form is still unclear, but it might suggest that black holes could have formed before the bulges in galaxies. In 2012, astronomers made another surprising discovery when they found a black hole in the galaxy NGC 1277, which is located 220 million light-years away in the Perseus constellation. This black hole was reported to have an unusually large mass of about 17 billion times the mass of the Sun. This mass is roughly 59% of the mass of the galaxy's bulge, which makes up 14% of the galaxy's total star mass. However, other research suggested a different result. The black hole might not be that large, with an estimated mass ranging from 2 billion to 5 billion times the mass of the Sun, with 5 billion being the most likely value. On February 28, 2013, astronomers used the NuSTAR satellite to measure the spin of a supermassive black hole for the first time. The black hole they studied was in the galaxy NGC 1365, and they found that its event horizon was spinning almost as fast as the speed of light. In September 2014, data from various X-ray telescopes showed that the very small, dense, and tightly packed galaxy M60 UCD1 contains a black hole at its center with a mass of 20 million times the mass of the Sun. This black hole makes up more than 10% of the total mass of the galaxy. This discovery was surprising because this black hole is 5 times more massive than the one at the center of our Milky Way galaxy, even though M60 UCD1 is less than 5,000ths the mass of the Milky Way. Some galaxies do not have supermassive black holes at their centers. While most galaxies without a supermassive black hole are small dwarf galaxies, one case remains puzzling. The supergiant elliptical galaxy, a 2261 BCG, which is one of the largest known galaxies, has not been found to contain an active supermassive black hole with a mass of at least 10 billion times the mass of the Sun, even though it is over 6 times the size and 1,000 times the mass of the Milky Way. However, several studies have suggested that the possible black hole at its center could have a mass anywhere between 6 billion and 10 billion times the mass of the Sun. This suggests that the galaxy might either have a black hole that is not actively growing, or one that is smaller than 10 billion times the mass of the Sun. In December 2017, astronomers reported the discovery of the most distant quasar ever found at that time, JWST 1342+0928, which contains the farthest supermassive black hole, with a redshift of 7.54. This beat the previous record held by the quasar JWST 1120+0641, which had a redshift of 7. In February 2020, astronomers announced the discovery of an eruption in the Ophiuchus supercluster, which was the most energetic event ever detected in the universe since the Big Bang. This happened in the Ophiuchus cluster, specifically in the galaxy Neve 1, where nearly 270 million times the mass of the Sun's material was being pulled into its central supermassive black hole, which has a mass of 7 billion times the Sun's mass. The eruption lasted around 100 million years and released 5 million times more energy than the most powerful gamma-ray burst ever seen. The eruption produced shockwaves and jets of high-energy particles that spread into the surrounding space, making a huge empty space about 1.5 million light-years wide, which is 10 times the size of the Milky Way. In February of the year 2021, a team of astronomers made an amazing announcement. They had made one of the most detailed images of the universe ever seen, an image that showed the locations of about 25,000 active supermassive black holes. These are not just ordinary black holes, but the giant ones that lie at the hearts of galaxies, each one millions or even billions of times heavier than our Sun. What made this image so special was not just the number of black holes it showed, but how it was made. It covered around 4% of the northern part of the sky, called the Northern Celestial Hemisphere. That may sound small, but in the vastness of space, it's still a huge area filled with cosmic wonders. To see these invisible giants, astronomers used a powerful tool called the Low Frequency Array, or LOFAR for short. This is a network of radio telescopes spread across several countries in Europe. LOFAR doesn't look at the sky the way our eyes do. Instead, it listens to the universe using very low-frequency radio waves, signals that are far below what the human ear could ever hear. These waves are perfect for spotting the powerful jets and bursts of energy coming from black holes that are swallowing matter. A stellar black hole, sometimes called a stellar mass black hole, is born in one of the most dramatic ways imaginable. It comes into existence when a massive star, much larger than our Sun, runs out of fuel and can no longer resist the crushing pull of its own gravity. At this moment, the core of the star collapses inward, squeezed under its enormous weight. This intense inward collapse is called a gravitational collapse, and it gives rise to one of the strangest and most powerful objects in the entire universe, a black hole. These black holes are not the huge giants found in the centers of galaxies. Instead, they are smaller, usually holding a mass between 5 and a few dozen times that of our Sun. But even though they are smaller, do not underestimate them. They still hold an unimaginable amount of power. Stellar black holes are the leftovers of massive stars that end their lives in spectacular explosions called supernovae. During these explosions, the outer layers of the star are hurled into space, while the core collapses inward. Some of these explosions are so violent that they send out bursts of gamma rays, which are the most energetic type of light in the universe. Because they come from collapsing stars, stellar black holes are sometimes called collapsers, a shortened term for collapsed stars. Even though black holes are born in violent, chaotic ways, physicists describe them as surprisingly simple objects. According to an idea known as the no-hair theorem, a black hole can be fully described by just 3 properties: its mass, how much matter it contains, its electric charge, if it has one, and its angular momentum, how fast it spins. If the original star was spinning, as most stars do, the resulting black hole will also spin, carrying over the rotation from its parent star. The creation of a black hole is a natural part of the life cycle of massive stars. As a star burns its nuclear fuel, the energy produced pushes outward, balancing the pull of gravity. But when the fuel runs out, the star loses this support. Gravity takes over, pulling everything inward. What happens next depends on the remaining mass of the star's core. If there is less mass, the core might become a white dwarf or a neutron star, both incredibly dense and compact remnants. In rare, still theoretical cases, the core could even become a quark star, made of tiny building blocks called quarks. However, if the leftover core is too heavy, it passes a point of no return known as the Tolman-Oppenheimer-Volkoff limit, often called the TOV limit. Once a star's core is heavier than this limit, nothing in the universe can stop it from collapsing. It continues shrinking until it forms a black hole, a region of space where gravity is so strong that even light cannot escape. Back in the year 1939, scientists estimated the TOV limit to be about 0.7 times the mass of our Sun. Later research, including a study from 1996, suggested the limit is likely somewhere between 1.5 and 3 times the mass of the Sun. One of the heaviest neutron stars ever found is called PSR J 0740+6620. Discovered in September of the year 2019, it weighs about 2.14 times the mass of the Sun. According to Albert Einstein's theory of general relativity, a black hole could theoretically have any mass, from very small to incredibly huge. But forming a very tiny black hole would require matter to be squeezed to extreme densities. In reality, no known star can collapse into a black hole smaller than a few times the mass of the Sun. If smaller black holes do exist, scientists believe they likely formed during the earliest moments after the Big Bang, rather than from dying stars. These are called primordial black holes. Until the year 2016, the largest stellar black hole known had a mass of about 15 2/3 times that of the Sun. But something extraordinary happened in September of the year 2015. Scientists detected gravitational waves, ripples in the fabric of space and time, from the collision of 2 smaller black holes. When they merged, they created a spinning black hole with a mass of about 62 times the mass of the Sun. This event provided some of the first direct evidence that black holes exist and that they can grow larger by merging. In June of the year 2020, scientists announced the discovery of the smallest stellar black hole ever found at that time. It is part of a binary system called 2MASS J 05215658+4359220. This tiny black hole has a mass of only 3.3 times the Sun's mass. Its diameter, about 19.5 kilometers across, smaller than many cities on Earth. Besides stellar black holes, astronomers have found signs of 2 other main types. Intermediate mass black holes may exist in the centers of globular clusters, which are tightly packed groups of stars. Supermassive black holes, on the other hand, reside at the hearts of almost every galaxy, including our Milky Way. These cosmic giants can be millions or even billions of times more massive than the Sun. Sometimes, a stellar black hole partners with a normal star in a cosmic dance called a binary system. When they orbit each other closely, the black hole can pull matter from its companion star. This matter spirals in toward the black hole, forming a hot glowing disk that can reach temperatures of hundreds of millions of degrees. At these temperatures, the matter emits X-rays, which scientists can detect with specialized telescopes. Even though the black hole itself remains invisible, these X-rays allow astronomers to see its presence. Meanwhile, the star-losing material can still be observed with regular telescopes. Neutron stars and black holes can sometimes act in ways that look surprisingly alike, especially when it comes to the enormous energy they release into space. But to tell them apart, scientists rely on careful measurements of their mass. Up to now, every neutron star that has been confirmed weighs less than 3 times the mass of our Sun. So, if astronomers find a mysterious, extremely compact object that is heavier than that and does not act like a neutron star, they can be fairly confident that it must be a black hole. Occasionally, astronomers come across pairs of stars or space objects, known as binary systems, in places where they really shouldn't be, far above or far below the flat plane of our Milky Way galaxy. This unusual positioning is thought to happen because of something called natal kicks. These are powerful jolts that occur when a black hole is born from the collapse of a dying star. Essentially, when a star dies and forms a black hole, it can get a strong push, sending it flying away from its original home. What is truly fascinating is that these black hole kicks often behave in a way very similar to the kicks given to neutron stars, even though black holes are much heavier. You might expect that because a black hole has so much mass, it wouldn't move very fast after getting a push. Yet, in reality, they often do move quickly. One possible explanation is that when a star collapses into a black hole, it does not throw off all its outer layers evenly. Some of that material falls back onto the new black hole, giving it an extra boost, almost like a cosmic afterburner that propels it faster through space. Scientists also believe that not all black holes are born in exactly the same way. Models of how stars live and die suggest that black holes within certain mass ranges may not be able to form directly from a collapsing star. These missing ranges are called mass gaps. There is one at the lower end and one at the upper end of the black hole mass scale. The lower mass gap is a puzzling space between about 2 and 5 times the mass of our Sun, where black holes appear to be rare or missing entirely. This is curious because it is just above the heaviest known neutron stars. Some scientists think this gap is real, while others argue that we simply haven't discovered enough black holes in this range yet. There is also a theory that black holes in this lower mass range might not be born from a single star collapsing, but instead could come from 2 neutron stars merging together. This is where facilities like the LIGO and Virgo observatories play a key role. They detect gravitational waves, tiny ripples in the fabric of space caused by massive cosmic collisions. So far, these observatories have detected 3 events that might involve black holes falling into this lower mass gap. Another intriguing clue comes from a strange star system, where a bright, rapidly spinning star seems to be orbiting an invisible companion. This companion does not give off light, not even X-rays, but its mass appears to be about 3.3 times that of the Sun. This could indicate a quiet, low-mass black hole that is not currently pulling in material, which is why we cannot see it. There could be many more such hidden black holes drifting through space unnoticed by us. Now let's look at the upper mass gap, a second mysterious range where black holes are surprisingly scarce. This gap is thought to lie between roughly 50 and 150 times the mass of the Sun, although some estimates place it between 52 and 133 solar masses. This upper mass gap is linked to a spectacular and violent type of explosion called a pair instability supernova. In such an event, an extremely massive star becomes so hot and energetic that gamma rays inside it collide with atomic particles, upsetting the delicate balance of pressure in its core. The result is a titanic explosion that completely tears the star apart, leaving no black hole behind. These rare explosions only happen in stars weighing between about 130 and 250 times the mass of the Sun, and mainly in stars made almost entirely of hydrogen and helium. These were the kinds of stars that existed billions of years ago, called population 3 stars, which are believed to have been the very first stars in the universe. Some newer ideas suggest that the upper mass gap might start at a slightly lower mass, maybe around 45 times the mass of the Sun, due to a process called pair instability pulsational mass loss. This happens before the supernova, when the star loses huge amounts of mass in giant pulses. For stars that are not spinning, the lower edge of this gap could be as high as 60 solar masses. There is also speculation that extremely massive stellar cores, those heavier than 133 times the mass of the Sun, might collapse directly into black holes without any explosion at all. If this is true, we would not see the bright remains of a supernova, which would make these events even harder to detect. This idea suggests that the beginning of the upper mass gap might mark the point where ordinary black hole formation stops. A few years ago, astronomers studying a system called LB1 thought they had discovered a black hole weighing about 70 times the mass of the Sun. If this were correct, it would have fallen right into the middle of the upper mass gap. But after further analysis, scientists began to question this finding. It might not have been a black hole at all. Even if black holes cannot be born directly into these mass gaps, they might still appear there later by merging. For example, if two smaller black holes collide and merge, the new black hole they create could fall right into one of these mysterious gaps. Closer to home, our Milky Way galaxy is full of candidates for stellar mass black holes. These black holes are formed from massive stars, not to be confused with the enormous supermassive black hole at the centre of our galaxy. Many of these stellar mass black holes are found in X-ray binary systems, where the black hole is stealing material from a nearby companion star. As this matter swirls into the black hole, it forms a glowing disk called an accretion disk, which releases powerful X-rays and makes the system much easier to detect. Scientists estimate that the black holes in these systems have masses ranging from about 3 to more than 12 times the mass of the Sun. The black hole called Sears 1019 is one of the strangest and smallest supermassive black holes ever found in the early universe. Even though it is about 9 million times heavier than our Sun, that is actually quite small compared to other supermassive black holes. Some of them can be as heavy as billions of times the mass of the Sun. Now here's where it gets really confusing. Scientists think it takes a very long time, much longer than 600 million years, for a black hole to grow that big. Usually black holes get bigger by pulling in gas, dust, stars, or even by joining with other black holes. But Sears 1019 seems to have grown very fast. Faster than current ideas can explain. To give you an idea, the black hole at the centre of our own Milky Way galaxy weighs about 4.5 million suns, and that one is found much later in the universe's history. So how could something even bigger exist when the universe was still so young? For many years, astronomers thought that supermassive black holes might have formed in the early universe, but they had no real proof. That changed when the James Webb Space Telescope, often called JWST, arrived. Thanks to its powerful infrared vision, JWST was finally able to see Sears 1019, and not only did it see it, it saw it eating. Yes, this black hole is actively pulling in matter around it. It swallows huge clouds of gas and dust, which spin around it in a giant disk called an accretion disk. The black hole's gravity heats this material so much that it shines brightly, almost like a cosmic diamond. But that's not all. While the black hole is eating, strong magnetic fields form and push some of the gas and energy toward its poles. From there, the material is shot out in two enormous jets that travel close to the speed of light. These jets shine brightly and can be seen from very far away. Astronomers saw the galaxy that holds this strange black hole during a special observation project called the Cosmic Evolution Early Release Science Survey, or SEERS for short. They were seeing this galaxy as it looked when the universe was only about 570 million years old. Remember, the universe today is about 13.8 billion years old, but Sears 1019 was not alone. Scientists also found two more black holes from around 1 billion and 1.1 billion years after the Big Bang, and 11 ancient galaxies that formed between 470 million and 675 million years after the universe began. What is amazing is that, until recently, most of what we knew about the early universe was just based on ideas, educated guesses really. But now, with the James Webb Space Telescope, scientists can actually see these faraway black holes and galaxies. Not only that, they can measure them too. And this isn't the only exciting discovery about black holes. In another study, scientists noticed something strange. Two stars were slowly changing their paths around nearby black holes. They were moving just a tiny bit slower every year, about 1 millisecond per year. That might not seem like much, but it could be very important. Why? Because researchers think the slowdown might be caused by dark matter, a mysterious type of matter that doesn't shine, reflect, or absorb light. In fact, we cannot see it at all, but we know it must exist because of how it affects things we can see. Let's break it down. Everything we can see in the universe, stars, planets, people, and galaxies, makes up only about 5% of the total universe. That's right, just 5%. The rest is made up of dark energy, around 68%, and dark matter, about 27%. Dark energy is thought to be the strange force that is pushing the universe to expand faster and faster. Dark matter, on the other hand, seems to hold galaxies together. Scientists know it must exist because they see its pull on stars and galaxies, but they still don't know exactly what it is. What dark matter isn't is just as important. It is not ordinary stars or planets. It is not clouds of gas, because we would be able to detect those. It is not antimatter, since we don't see the special gamma rays that antimatter produces when it touches normal matter. And it is probably not giant black holes either. So what is it? No one knows for sure. Some ideas suggest it could be made of strange particles we haven't found yet. Others think it could be faint objects that hardly shine. But whatever it is still one of the biggest mysteries in space. Now, back to those two stars slowing down. Scientists ran computer models of the black hole systems and used an idea called the dark matter dynamic friction model. This idea says that when normal matter, like stars, moves through dark matter, it can slow down because of the gravitational drag from the dark matter. And guess what? The models matched what the scientists saw in real life. This supports the idea that black holes might actually pull in dark matter that gets too close. And as they do, dark matter might form thicker areas around black holes, which could then change how nearby stars move. If these findings are confirmed, it could be a big step forward in understanding dark matter, one of the most mysterious parts of our universe. We have been talking a lot about black holes lately, but here's something even stranger. There is an interesting idea that a very special kind of black hole, called a primordial black hole, might actually be the key to solving one of the biggest mysteries in space: dark matter. Primordial black holes are completely theoretical. That means scientists have never actually seen one or found proof that they exist. But if they do, they are thought to be extremely old and very, very small, at least for black holes. Astronomers think these black holes could have formed just a few milliseconds after the Big Bang, which happened around 13.8 billion years ago. At that time, the universe was just born. There were no stars, no galaxies, not even atoms like we know today. Everything was just a hot, dense soup of energy and particles. If primordial black holes really formed back then, that means they have been around for the whole history of the universe. They have seen it all, from the first stars lighting up the sky, to the birth of galaxies and even the rise of life on planets like Earth. The smallest of these early black holes have probably disappeared by now, slowly evaporating over time through a process called Hawking radiation. But the bigger ones, the ones that started with more mass, might still be drifting quietly through space, hidden in the dark. So how did they form at all? Scientists think the early universe wasn't perfectly smooth. Some places were hotter, some cooler, and some spots were very dense. In those dense patches, gravity could have become strong enough to crush matter into tiny black holes. These became the primordial black holes. What is even more amazing is this: because they formed so early, they stayed small. The rule seems to be, the earlier a black hole forms, the smaller it is. A black hole that formed a little later might have been 1,000 times heavier than our Sun, while a primordial one could be as tiny as a pea or even smaller. The difference in weight is incredible. For a long time, most scientists didn't take this idea seriously. The idea that primordial black holes could actually be dark matter was ignored for decades. Dark matter, after all, is the invisible stuff that makes up most of the matter in the universe, and no one has been able to find a single dark matter particle, even after many years of searching. But things have changed. In recent years, astronomers have started to see that there might be far more black holes in the universe than they ever imagined. This surprising discovery has made some scientists look again at primordial black holes. Maybe, just maybe, these ancient hidden objects aren't just hiding. They could actually be dark matter itself. Cygnus X1 is one of the most famous discoveries in space in the history of astronomy. This strong source of X-rays is found in the constellation Cygnus, also called the Swan. What makes Cygnus X1 so special is that it was the very first object in our galaxy to be widely accepted as a black hole. Its discovery opened the door to a new understanding of the universe. The story began in the year 1964, when scientists sent a rocket to look at the sky beyond Earth's atmosphere. During that mission, they detected incredibly strong X-rays coming from the direction of Cygnus. This strange signal quickly got the attention of astronomers, because it was one of the strongest X-ray sources ever seen from Earth. The X-ray signal had a peak power of about 2.3 times 10 to the negative 23rd watts per square meter per hertz, or, more simply, around 2,300 Janskis. Today, Cygnus X1 is still one of the most closely studied objects of its type. At the centre of this system is a mysterious, extremely dense object, with a mass estimated to be about 21 times the mass of our Sun. This object is far too small to be any normal star, and its extreme properties match only one known thing: a black hole. If this is true, then its event horizon, the invisible edge around the black hole, would have a radius of no more than 300 kilometers. That's the biggest size scientists can calculate based on very short X-ray flashes that last just 1,000th of a second. Cygnus X1 is actually part of a binary system, a pair of objects held together by gravity. The second member of this space pair is a massive blue supergiant star. Together they make what's called a high-mass X-ray binary system. This amazing pair is about 7,000 light-years from Earth. The distance between the two members of this system is only about 1/5 the distance from the Earth to the Sun, which is roughly 0.2 astronomical units. The giant star sends out strong winds full of gas, and some of this material is pulled in by the black hole. The gas forms a spinning disk around the black hole called an accretion disk. As the gas moves inward, it heats up to millions of degrees and gives off strong X-rays. In addition, two thin, fast jets of energy shoot out from the disk in opposite directions, sending material far into space. Scientists think that Cygnus X1 might be part of a nearby group of massive young stars called Cygnus OB3. If this is true, then the system is about 5 million years old. The black hole probably formed from a huge star that originally weighed more than 40 times the mass of the Sun. This giant star lost most of its mass through stellar winds and may not have exploded in a bright supernova. Instead, it may have quietly collapsed directly into a black hole. The fame of Cygnus X1 also reached beyond science. In 1975, two famous physicists, Stephen Hawking and Kip Thorne, made a friendly bet about its true nature. Hawking bet that it wasn't a black hole, even though he hoped to be proven wrong. In 1990, Hawking admitted he lost, as the evidence strongly supported that Cygnus X1 really is a black hole. The visible star in the system, named HDE 226868, is a supergiant on its own, but could not produce the X-rays we see by itself. This led astronomers to suspect a hidden, compact companion. In 1972, Louise Webster and Paul Murdin from the Royal Greenwich Observatory, along with Charles Thomas Bolton from the University of Toronto's David Dunlop Observatory, independently confirmed the existence of this mysterious object. They studied the light spectrum of HDE 226868 and noticed it was shifting slightly in colour. This effect, called Doppler shifting, showed that the star was wobbling because of the gravitational pull of a massive unseen companion. Using this data, scientists estimated the companion's mass and concluded it could not be a neutron star because it was far too heavy. The only explanation left was that it had to be a black hole. By the end of 1973, most astronomers agreed that Cygnus X1 was very likely a black hole. Later studies showed that the system's X-ray brightness could change in as little as 1 millisecond, just 1,000th of a second. This matched what was expected for a spinning accretion disk around a black hole. Some X-ray bursts lasted about 1/3 of a second, which fits with the time it would take for material to fall into a black hole. Since then, Cygnus X1 has been observed using many instruments on Earth and in space. The similarities between systems like Cygnus X1 and the bright cores of faraway galaxies, called active galactic nuclei, suggest they might work in the same way. This has led scientists to put Cygnus X1 in a special category called microquasars. These are smaller versions of quasars, the bright and energetic objects at the centres of galaxies, all powered by black holes, accretion disks and jets. The black hole and the supergiant star orbit each other once every 5.6 days. From Earth, the black hole never passes directly behind the star, so the system doesn't eclipse. Scientists are still figuring out the exact tilt of the orbit, with estimates from 27 to 65 degrees. In 2007, one study estimated the tilt to be around 48 degrees, with an error of about 7 degrees. This supports the idea that the two objects are separated by about 1/5 of the Earth-Sun distance. Their orbit is nearly circular, with a tiny eccentricity of about 0.018. Looking far ahead, Scientists think that in about 5 billion years, the supergiant and black hole may merge into a bigger black hole, possibly creating strong ripples in spacetime called gravitational waves. Both HDE 226868 and Cygnus X1 seem to be moving through space together with the Cygnus OB3 group, about 7,000 light-years away. This strongly suggests that they were all born in the same star nursery around 5 million years ago. The star HDE 2268. 68 is now about 60 parsecs, or roughly 200 light-years, from the centre of the Cygnus OB3 group, a distance it could have travelled in about 7 million years, matching the group's estimated age. The distance to Cygnus X1 has been measured in two ways. Using trigonometric parallax, it was estimated at about 1,860 parsecs, roughly 6,070 light-years. Another method, called radioastrometry, gave a distance of around 2,220 parsecs, or about 7,240 light-years. In our galaxy, Cygnus X1 is along the Orion Spur, the same spiral arm of the Milky Way where our Sun is located. It is also close to the Sagittarius Arm, another big group of stars and gas. Some scientists even think Cygnus X1 is part of the Sagittarius Arm, though the exact shape of the Milky Way is still being studied. Astronomers have used different methods to measure the mass of the mysterious supercompact object at the heart of Cygnus X1. No matter the method, they all agreed on one thing: the object is far too heavy to be a neutron star. That's a strong clue that it's a black hole. Early models of how stars change over time suggested this object might weigh about 20 times as much as our Sun, plus or minus 5 solar masses. Other methods gave a lower estimate of about 10 times the Sun's mass. But by studying the flickering X-ray signals, scientists made a more accurate estimate, about 14.8 solar masses with a possible error of just 1 solar mass. All these numbers still pointed to the same conclusion. This object is most likely a black hole, a place in space where gravity is so strong that nothing, not even light, can escape. The invisible edge marking the point of no return is called the event horizon. For Cygnus X1, this event horizon is thought to be about 44 kilometers wide. Anything that crosses it, light, gas, or even stars, can never come back. In 2021, new measurements gave a slightly higher mass, about 21.2 solar masses, with an uncertainty of plus or minus 2.2. Then, in 2025, another study suggested a mass of about 17.5 solar masses, though that might just be the maximum. Another method gave a similar result of 13.8 times the Sun's mass. Back in 1992, scientists may have glimpsed the black hole's event horizon using ultraviolet light, thanks to the high-speed photometer on the Hubble Space Telescope. As glowing clumps of matter spiraled into the black hole, their light stretched to longer wavelengths. This effect, called gravitational redshift, was exactly what Einstein's theory predicted. If these clumps had hit something solid, they would have given off a bright final burst of energy, but they didn't. Instead, two strange patterns of fading pulses, called dying pulse trains, were seen. That's strong evidence that these clumps disappeared beyond an event horizon, just as expected for a black hole. For a long time, scientists weren't sure whether the compact object was spinning or not. Data from NASA's Chandra X-ray Observatory once suggested it wasn't rotating much at all. But then, in the year 2011, new evidence showed that it might actually be spinning at an incredible speed, about 790 times every single second. Cygnus X1 is part of a group of stars known as the Cygnus OB3 Association. The biggest star in that group weighs about 40 times as much as our Sun. Because heavier stars burn through their fuel faster, this suggests that the star which collapsed into the Cygnus X1 black hole must have been even bigger, maybe over 40 times the Sun's mass. That means it lost more than 30 times the Sun's mass of material before collapsing. Some of that mass may have moved to its companion star, HDE 226868, while the rest was likely blown away in strong stellar winds. Interestingly, the outer layers of HDE 226868 have extra helium, which may be leftover material from that earlier mass transfer. The original star may even have gone through a Wolf-Rayet phase, a late stage where the star loses huge amounts of gas through powerful winds. Usually, when a massive star dies, it explodes as a supernova. But if that had happened here, the explosion would likely have thrown the black hole out of its orbit. Since it stayed in place, scientists think the star may have skipped the explosion completely and collapsed straight into a black hole, or at most caused only a small, quiet explosion. Around the black hole there's a thin, flat ring of matter called an accretion disk. This disk is made of gas spiraling inward, getting extremely hot from friction as it falls. The inner part of the disk is very hot and full of charged particles, forming a state of matter called plasma. The outer part is cooler and stretches out to about 15,000 kilometers, about 500 times the size of the black hole's event horizon. Cygnus X1 is one of the brightest sources of high-energy X-rays in the sky. These X-rays, which carry energies from about 30 to several hundred kilo-electron-volts, are made when lower-energy photons are supercharged. This happens in two ways, either by bouncing off superhot electrons in a see-through layer of gas called the corona that surrounds the disk, or possibly by scattering from the base of a jet of particles shooting out from the black hole. The X-rays from Cygnus X1 also show a strange rhythm called quasi-periodic oscillations, or QPOs. These flickers seem to depend on how heavy the black hole is. The heavier it is, the closer to the center the flickering starts. This gives scientists another way to double-check the black hole's mass. What's more, Cygnus X1 doesn't act like neutron stars. Neutron stars usually pulse with regular beats, or sometimes produce short, explosive bursts of X-rays, but Cygnus X1 does neither. It also switches between two different X-ray states, a hard state and a soft state. In the hard state, most of the X-rays are very energetic. In the soft state, they are less energetic but more unpredictable. The hard state comes from the hot corona, while the soft state happens when the disk moves closer to the black hole and the corona disappears or cools down. When the corona forms again, the system flips back to the hard state. One explanation for these changes comes from a model called the two-component advective flow. In this idea, the hard X-rays are created by scattering seed photons from the disk and other high-energy photons made by fast-moving electrons in a region called the CENBL, centrifugal pressure-supported boundary layer. The amount of X-ray light also changes in a regular cycle every 5.6 days, especially when the black hole is behind its companion star as seen from Earth. This suggests that the X-rays are partly blocked by gas from HDE 226868 strong wind. There's also a longer 300-day cycle, which might be caused by the slow wobbling or precession of the accretion disk. As matter falls toward the black hole, it loses energy. Some of that energy escapes in two narrow jets shooting out from the black hole's poles. These jets move at speeds close to the speed of light and carry away extra energy and spin. Magnetic fields in the gas may help shape and launch these jets. Interestingly, these jets don't give off much visible light or radiation, so they're considered dark. One of the jets seems to be hitting a dense cloud in space, creating a glowing ring of energy that can be seen in radio waves and visible light. The power needed to make this nebula is estimated to be between 4 and 14 times 10 to the power of 36 ergs per second, or roughly 9 times 10 to the power of 29 watts. That's over 1,000 times more powerful than all the energy the Sun gives off. Because the opposite jet is travelling into a less dense part of space, no ring is seen on that side. In the year 2006, Cygnus X1 made history again. It became the first stellar mass black hole known to give off gamma rays at extremely high energies, above 100 giga-electron volts. These powerful rays were detected at the same time as a burst of high-energy X-rays, suggesting both events may have come from the same process. The X-rays may have come from near the base of the jet, while the gamma rays were likely made when the jet hit the strong wind from HDE 26868. Now, about that companion star, HDE 226868. It's a blue supergiant and belongs to a class of stars called 09.7 IAB, which sits on the edge between two major stellar groups, Class O and Class B. This star has a surface temperature of about 31,000 degrees Kelvin and a mass estimated to be between 20 and 40 times the Sun's mass. If it really is about 2,000 parsecs away, that's over 6,500 light-years, it may have a radius about 15 to 17 times larger than our Sun and shine with 300,000 to 400,000 times more brightness. The black hole orbits HDE 226868 at a distance of around 40 times the Sun's radius, twice the size of the supergiant star itself. The gravity from the black hole stretches the surface of HDE 226868 into a teardrop shape, which also rotates, causing the star's brightness to change slightly, by about 0.06 magnitudes, every 5.6 days as the stars orbit each other. This light change is caused by the way different parts of the star's surface appear brighter or dimmer because of gravity and angle. Compared to another bright star called Alnilam, HDE 26868 has more helium and less carbon in its outer layers. Its ultraviolet light and hydrogen alpha lines look similar to those seen from Pkygne, which means the star is surrounded by a cloud of gas that's being blown away at speeds of about 1,500 kilometers per second. Like other big stars, HDE 26868 is constantly losing mass through a strong stellar wind, at a rate of about 2.5 millionths of a solar mass per year. That's equal to losing one whole sun's mass every 400,000 years. The nearby black hole's gravity is reshaping this wind, making it flow in a more focused stream instead of spreading out evenly. The X-rays coming from the black hole's surroundings heat and charge this wind. As the black hole moves through the wind in its 5.6-day orbit, the ultraviolet light, radio signals, and X-rays it gives off all change. The star has a gravitational boundary called the Roche lobe. Material that stays inside this zone remains part of the star, but if it crosses the line, it might fall toward the black hole. In this case, the Roche lobe seems very close to the star's surface, but not quite overflowing, so the black hole isn't taking material directly from the star. However, a good amount of the stellar wind does pass beyond the lobe and gets pulled into the accretion disk. However, all the gas and dust floating between Earth and HDE 26868 dims the star's light and makes it look redder than it really is. This effect is called interstellar extinction, and for this star it's about 3.3 magnitudes. Without this dusty veil, HDE 26868 would be a 5th magnitude star just bright enough to be seen with the naked eye. Black holes come in all shapes and sizes, and one of the most mysterious kinds is called an intermediate mass black hole, often shortened to IMBH. These black holes are not tiny, but they are not enormous either. They sit right in the middle. Their weight can range from about 100 times the mass of our Sun to as much as 100,000 suns. That makes them much heavier than the typical black holes formed when massive stars collapse, known as stellar black holes, yet still far smaller than the supermassive black holes that dominate the centers of galaxies, which can weigh more than 1 billion suns. Over time, astronomers have spotted a few possible examples of these medium-sized black holes, both inside our own Milky Way and in nearby galaxies. Interestingly, scientists haven't actually seen these black holes directly. Instead, they looked at how nearby gas clouds move, or they studied the light coming from the spinning disks of superheated matter, called accretion disks, that form when black holes pull in material. These indirect clues gave astronomers good reason to believe that IMBHs are lurking in certain cosmic locations. One of the most thrilling moments in the search for IMBHs came from ripples in spacetime itself. On the 21st of May in the year 2019, at exactly 3 minutes and 2 seconds past 3 in the morning Coordinated Universal Time, scientists detected a powerful gravitational wave, which they named GW 190521. This signal came from the collision of two black holes, one weighing about 85 suns, the other about 65 suns. When they merged, they formed a new black hole with a mass of 142 suns. The missing mass, around 8 suns, was released as energy in the form of gravitational waves, shaking the very fabric of space-time. This incredible discovery was shared with the world on the 2nd of September in the year 2020. Before this, the strongest hints of IMBHs came from certain galaxies called low-luminosity active galactic nuclei. These galaxies glow faintly, and their strange behavior suggests there could be black holes at their centers. In some cases, astronomers could even estimate the black hole's size using a method called reverberation mapping, which measures how light echoes off gas near the black hole. One striking example is a spiral galaxy called NGC 4395, located about 4 million parsecs away. At its center, there appears to be a black hole weighing around 360,000 suns. A huge collection of potential intermediate mass black holes, 305 in total, was identified after a deep study of roughly 1 million galaxy light readings, collected from a large project called the Sloan Digital Sky Survey. Of these 305 candidates, 10 were giving off X-rays, providing strong support that they might indeed be intermediate mass black holes. Another exciting place to hunt for IMBHs is among mysterious objects known as ultra-luminous X-ray sources, or ULXs. These are incredibly bright spots in the X-ray sky, often appearing in galaxies where new stars are being born, like the famous starburst galaxy M82. ULXs usually sit near clusters of young stars, and scientists think they might be black holes feeding on nearby stars. To prove that a ULX hides an IMBH, astronomers must carefully study the light from its companion star and track its movement. Some researchers also suspect that IMBHs could be hiding inside globular clusters, tight spherical groups of stars that orbit around galaxies like our Milky Way. To search for black holes in these clusters, astronomers measure how the stars at the centre are moving. If a massive black hole is present, it would disturb the motion of nearby stars. So far, none of the supposed discoveries have stood up to further scrutiny. One example is a cluster called M31G1. Initially, it seemed to contain a large black hole, but later studies showed that the star movements could be explained without needing one at all. Gravitational waves may eventually unlock this cosmic mystery. If an intermediate mass black hole partners with another black hole, or even a dense object like a neutron star, their spiraling dance toward collision would send ripples through space-time, detectable by instruments such as LIGO and Virgo. There is also a mathematical guideline known as the M-sigma relation, which predicts a black hole's size based on how stars move around a galaxy's centre. According to this rule, smaller galaxies with dim centres are expected to host black holes weighing between 10,000 and 1 million suns. The smallest black hole predicted this way is in a galaxy called RGG 118, weighing about 50,000 suns. Back in November of the year 2004, astronomers announced a remarkable finding. They had discovered what they believed to be the first intermediate mass black hole in the Milky Way. Named JWST 13e, it weighs around 1,300 suns and sits just 3 light-years from the Milky Way's giant central black hole, Sagittarius A. JWST 13e is part of a cluster of 7 stars, which might be the remnants of a larger star cluster torn apart by the strong gravity near the galaxy's centre. This discovery supported the idea that supermassive black holes may grow gradually by swallowing smaller black holes and stars. However, not everyone agreed. In the following year, 2005, a German research team raised doubts. They studied the star's movements in that cluster and suggested there might not be a black hole there after all. If an IMBH is really orbiting close to the galaxy's centre, it could potentially be detected by observing how it affects the motions of nearby stars. Then, in January of the year 2006, a team led by Philip Carrot from the University of Iowa made another exciting announcement. They discovered a repeating signal, known as a quasi-periodic oscillation, coming from a possible black hole in galaxy M82. This object, named M82X1, seems to be feeding on a red giant star that is slowly losing its outer layers. The discovery was made using NASA's Rossi X-ray Timing Explorer satellite. Even so, this discovery was not fully confirmed. The signal only completed about 4 cycles, which might not be enough to prove it was truly repeating. It could have been random background noise, and even if the signal is real, scientists still do not know whether it is caused by the star's orbit or by slower processes in the black hole's accretion disk. In the year 2009, astronomer Sean Farrell and his team made another big discovery. They found a strange object called HLX-1, which turned out to be a medium-sized black hole. What made HLX-1 so interesting was that it seemed to be surrounded by a small group of stars, almost like its own tiny galaxy. HLX-1 was located inside a bigger galaxy called ESO 24349, and the scientists thought this galaxy had once collided with a smaller galaxy that carried HLX-1. Most of the smaller galaxy's stars were absorbed, but the black hole stayed. A few years later, on the 9th of July 2012, scientists using a radio telescope run by CSIRO in Australia announced another important discovery. They believed they had found the first clear example of a medium-sized black hole, based on strong radio signals. Then, in the year 2015, researchers at Keio University in Japan saw something surprising. They were studying a strange gas cloud called CO 0.400.22 and noticed that the gas particles were moving at very different speeds. After running computer simulations, they concluded that the best explanation was a black hole weighing about 100,000 times the mass of our Sun. But even this wasn't certain. Later studies suggested that the gas cloud's strange behaviour might also be caused by shock waves from exploding stars known as supernovae. So the mystery continued. Back in the year 2017, scientists thought they had made an exciting discovery. They believed they had found a black hole hiding deep inside a giant group of stars called a globular cluster. This cluster is called 47 Tucani and is in the southern sky. The black hole they suspected was not like the usual small ones formed when massive stars die. Instead, it seemed to be a mysterious in-between type, a medium-sized black hole, possibly weighing a few thousand times more than our Sun. This idea came from looking at how special spinning stars called pulsars were moving. Their speed and direction suggested that something very heavy might be pulling on them, but later, more precise observations could not find solid proof of any black hole there. Then came the year 2018, and once again, scientists from Keio University in Japan were in the spotlight. This time, they found several streams of cold gas circling around something invisible near the centre of our Milky Way galaxy. This hidden object, with the technical name HCN 0.0090.044, was estimated to have the mass of about 32,000 suns. If confirmed, it would be the third known black hole in that puzzling middle range, too big to come from a single star but not large enough to be called supermassive. Just a year later, in 2019, a dramatic cosmic event caught scientists' attention. They detected gravitational waves, ripples in space and time, caused by two black holes crashing into each other. One black hole weighed about 66 times the Sun, and the other about 85 times the Sun. When they collided, they merged into a new black hole roughly 142 times heavier than the Sun. Around 9 times the Sun's massive energy was released as gravitational waves. This event, called GW190521, added another clue in the search for medium-sized black holes. In the year 2020, astronomers may have found another one of these mysterious objects. They found a possible black hole called 3XMMJ 21502 2.4055108. This candidate is in the direction of the Aquarius constellation and is about 740 million light-years away. Again, it could be a medium-sized black hole. The next year, in 2021, there was another exciting announcement. Scientists reported finding a black hole weighing around 100,000 times the mass of the Sun. It was inside a globular cluster called B023G78 in the Andromeda Galaxy. The discovery was first shared in a scientific preprint but quickly drew attention worldwide. Then, in 2023, astronomers looked closely at Messier 4, the closest globular cluster to Earth. They noticed the stars in this cluster were moving strangely, as if something very heavy and compact sat at the centre. This mysterious object seemed about 800 times heavier than the Sun. Because it was so tightly packed and didn't spread out like normal stars, scientists thought it might be a black hole. But they couldn't be completely sure. It could also be a group of white dwarfs, neutron stars, or small black holes clustered together. On the 10th of July in 2024, another interesting study made headlines. This one looked at 7 stars in a cluster called Omega Centauri. These stars were moving very fast as if they were orbiting something heavy and invisible. The hidden object's mass was estimated at least 8,200 times the Sun, another strong candidate for a medium-sized black hole. Here's where things get really tricky. These middle-sized black holes don't follow the usual rules. They're too big to form the way smaller black holes do, which happens when a single star explodes in a supernova and collapses. Yet, they are also too small to form like supermassive black holes, those giants in the crowded centres of galaxies. So how do medium-sized black holes form? Scientists have a few ideas. One idea is that many smaller black holes, over millions or billions of years, slowly merge to make a bigger one. Another is that, in very crowded clusters, several huge stars might crash into each other. The result could be a massive star that collapses into a medium black hole. A more unusual idea is that these black holes formed shortly after the universe began, soon after the Big Bang, making them what scientists call primordial black holes. There's also debate about whether a single enormous star could collapse directly into a medium black hole. For this, the star would need to be extremely massive, at least 260 times the Sun. Some scientists think this could happen if several stars in a young, crowded cluster merged into one giant star. If that giant star then collapsed, it might make a medium-sized black hole, but events like this would be very rare and hard to catch, making them one of the universe's best-kept secrets. Long before the first stars lit up the universe, when everything around us was still incredibly young, just a tiny fraction of a second old, some scientists think that a very unusual kind of black hole might have formed. These are called primordial black holes, often shortened to PBHs. Unlike the black holes we see today, primordial black holes are strange and mysterious, and they might hold secrets about the universe that no one has yet unlocked. Most black holes we know are born from the death of massive stars. When a giant star runs out of fuel, it can no longer hold itself up against its own gravity. The star explodes in a supernova, and its heavy core collapses inward, forming a black hole. But primordial black holes are thought to have formed in a completely different way, long before any stars even existed. In the first moments after the Big Bang, the universe was unimaginably hot and filled with radiation, and tiny particles moving almost at the speed of light. During this period, known as the inflationary era, tiny but extremely dense clumps of matter may have been crushed under their own gravity. These clumps were not made from stars. They may have collapsed directly into black holes, forming just milliseconds after the universe began. This means primordial black holes could have existed far before stars, galaxies, or even the atoms we're made of. Because they did not come from stars, primordial black holes don't follow the same patterns as the regular black holes we see today. Most black holes we know are only a few times heavier than our Sun, but PBHs could be almost any size. Some might be smaller than a single atom, while others could weigh thousands of times more than the Sun. Their sizes could vary in almost every way imaginable. The idea of primordial black holes was first suggested in 1966 by two Soviet physicists, Yakov Zeldovich and Igor Novikov. A few years later, in 1971, the young British physicist Stephen Hawking explored the idea further, imagining what would happen if black holes really could form in the very early universe. Even today, more than 50 years later, primordial black holes remain just a theory. Scientists have yet to find direct proof of them, but there are many clues suggesting they could exist. In September of 2022, a group of scientists proposed that PBHs might explain a surprising discovery made by the James Webb Space Telescope. The telescope had spotted massive galaxies forming extremely early in the universe, much earlier than anyone thought possible. Primordial black holes could have acted as seeds, pulling in surrounding matter and helping these galaxies grow quickly. Some researchers have even suggested that primordial black holes could help solve one of the biggest mysteries in science: dark matter. Dark matter is an invisible kind of matter that doesn't emit light, so we cannot see it with any telescope, yet it seems to make up most of the matter in the universe. If PBHs are common enough, they might account for nearly all of this invisible matter. Support for this idea has grown in recent years, especially thanks to the LIGO and Virgo detectors, which can hear gravitational waves, ripples in space created when black holes collide. Observations from the James Webb Space Telescope have also given hints that seem to fit the PBH theory. At first, scientists thought that if primordial black holes existed, they would all be about the same size, a concept called a monochromatic mass distribution. But data from LIGO and Virgo changed this view, showing that black holes come in many different sizes. New findings from the James Webb Telescope also suggest that primordial black holes could have a wide range of masses, with many similar in weight to our Sun. Some primordial black holes might be incredibly tiny, perhaps as small as an asteroid, yet containing the mass of something as dense as a hydrogen atom. These tiny black holes could zip through space at incredible speeds. In fact, it is possible that one might even be travelling inside our solar system right now. Usually, if such a small black hole passed through a star, it would go straight through, like a bullet-piercing fog. But if it moved slowly enough, it could get trapped by the star's gravity. Hawking even once suggested that our Sun might be hiding one of these tiny black holes inside it. Depending on the theory, a primordial black hole might have started with a mass as small as 10 to the -8 kilograms, what scientists call a Planck relic, or it could have been thousands of times heavier than the Sun. However, PBHs that began with a mass smaller than 100 billion kilograms probably no longer exist. Over billions of years, they would have slowly evaporated due to a mysterious process known as Hawking radiation, where small black holes gradually disappear. only the larger primordial black holes would still be around today. Primordial black holes are also different from ordinary matter, like the kind that makes up stars, planets, and people. They might be made of non-baryonic matter, which does not follow the same rules as regular atoms. This is another reason why some scientists think PBHs could be connected to dark matter. Some researchers believe these early black holes might have even helped create the supermassive black holes at the centers of massive galaxies, or the intermediate-sized black holes in smaller galaxies. In this sense, primordial black holes could have been the original seeds from which some of the universe's largest black holes grew. PBHs also belong to a larger group of mysterious objects called MACHOs, which stands for Massive Compact Halo Objects. These are massive dark objects that move slowly through space and rarely collide with other things, making them excellent dark matter candidates. Some MACHOs may have formed within the first second after the Big Bang. Not all scientists agree on these ideas. Some observations of space suggest there cannot be too many primordial black holes, or we would have already detected them. These scientists believe PBHs probably make up only a small fraction of dark matter, yet others think they could play an important role, especially if they tend to cluster together. In fact, there could even be a primordial black hole weighing about 30 times the Sun's mass sitting at the center of each cluster. In March of the year 2016, just 1 month after scientists said they had detected gravitational waves for the very first time using the improved Advanced LIGO and Virgo detectors, 3 different research groups shared an exciting idea. Maybe those waves came from 2 primordial black holes merging together. Each of these black holes had about 30 times the mass of our Sun, which was very surprising. 2 of the groups said this was exactly what we would expect if PBHs made up all the dark matter, but only if they were hiding in small groups of stars like faint dwarf galaxies or globular clusters. The 3rd group disagreed. They said the number of mergers seen by LIGO was too low, and that PBHs could only make up less than 1% of the dark matter in the universe. The unexpectedly large black holes found by LIGO brought new attention to the idea of PBHs with masses between 1 and 100 times the mass of the Sun. Scientists are still trying to figure out whether this idea fits with other observations, like the lack of microlensing events, patterns in the cosmic microwave background, the size of tiny galaxies, and the missing X-ray and radio signals near the center of our galaxy. In May of the year 2016, a scientist named Alexander Kashlinsky shared a truly fascinating idea with the world. While carefully studying the universe's background radiation, the faint afterglow of ancient cosmic events, he noticed something strange. In particular, he found unusual patterns in gamma rays and X-rays coming from parts of the sky where no visible objects like stars or galaxies could be seen. It was as if something invisible was shining through the darkness. These strange signals puzzled scientists for years. Kashlinsky suggested a bold explanation. He believed these mysterious rays might actually come from primordial black holes, extremely ancient black holes that may have formed just tiny fractions of a second after the Big Bang, long before the first stars were born. He even suggested that if these black holes were all about the same size and were as common as dark matter, they might be the source of this unexplained radiation. It was an exciting possibility, one that could link black holes to one of the biggest mysteries in all of science. Then, in August of the year 2019, another scientific study offered an even more amazing idea. This new research suggested that all the dark matter in the universe, the invisible stuff that makes up most of the mass in space, might actually be made entirely of primordial black holes, and not giant ones either. These would be black holes about the size of asteroids, small but incredibly heavy. Imagine countless tiny but dense black holes scattered throughout space, quietly making up most of the universe's unseen mass. It was a daring idea that sparked a wave of curiosity. Only 1 month later, in September of the same year, 2019, 2 scientists named James Unwin and Jakub Schultz came up with yet another surprising idea. They thought there might be a black hole hiding inside our own solar system. According to them, this black hole could have a mass between 5 and 15 times the mass of the Earth. But it wouldn't be a giant monster. Amazingly, it might be no bigger than a tennis ball. This incredibly compact object could be sitting far beyond the planet Neptune, in a distant region called the Kuiper Belt. Their idea was based on something strange. A few faraway space objects were moving in unusual, unexpected ways. It looked like something massive but invisible was pulling on them. For years, scientists had been searching for a mysterious Planet 9 that might be causing this. But Unwin and Schultz had a bold new idea. Maybe Planet 9 wasn't a planet at all. Maybe it was a primordial black hole. In October of the year 2019, scientists Derek Inman and Yassine Ali Haimoud studied how the large structure of the universe might affect what we know about something called the cosmic microwave background, CMB. The CMB is the faint radiation left over from the Big Bang, like an ancient echo frozen in time. Their research showed that the small shifts in matter that happened as galaxies formed were not strong enough to change what we know from the CMB. That meant scientists could still trust the CMB data when studying black holes and the early universe. It was still a solid base for discovery. Jump ahead to September of the year 2021. A team of scientists from the Nanograv collaboration made an exciting announcement. They had picked up a low-frequency signal that could be linked to gravitational waves, tiny ripples in the fabric of space and time itself. Some researchers thought that this gentle hum across the universe might come from groups of primordial black holes. If true, this would give us a new way to detect these ancient cosmic ghosts, even though they're normally invisible. Then, in September of the following year, 2022, scientists again focused on primordial black holes. This time, they were trying to solve a new puzzle. The powerful James Webb Space Telescope, one of the most advanced space telescopes ever built, had seen huge galaxies forming far too early in the universe's history, just a few 100 million years after the Big Bang. According to current theories, galaxies that big shouldn't have formed so soon. But if primordial black holes had helped galaxies grow faster and earlier than expected, then these early giants suddenly made more sense. A few months later, on the 26th day of November in the year 2023, scientists made a discovery that amazed the astronomy world. For the first time ever, they found strong evidence of something called an overmassive black hole galaxy, or OBG. This kind of galaxy may have formed in a very rare way through a process called direct collapse. Instead of being born from the death of a star, this black hole formed straight from a huge cloud of gas, skipping the usual steps. The galaxy where this happened was a faraway one called UHZ-1, and at its center was a blindingly bright quasar, a powerful object powered by a supermassive black hole. Scientists used both the Chandra X-ray Observatory and the James Webb Space Telescope to study it. The discovery opened a new chapter in understanding how black holes and even galaxies might form. In the year 2024, a group of researchers led by physicist Bernard Carr took a new look at how primordial black holes might have first appeared. Their review focused on a tiny moment in time called the quantum chromodynamics epoch, which happened less than 100,000th of a second after the Big Bang. According to their findings, the black holes formed during this moment would follow a special pattern in their sizes today, with certain bumps or peaks in mass. One of these bumps was near one solar mass, which is about the same mass as our Sun. But how could such ancient black holes have formed in the first place? Scientists think that primordial black holes might have appeared within the very first second after the Big Bang. They could have formed during the inflationary era, a period when the universe expanded incredibly fast, or early in the radiation-dominated era, when light and energy filled space. For a black hole to form, you need a very dense area of matter, where gravity becomes so strong that everything collapses inward. These dense pockets might have been caused by tiny differences in how matter was spread out in the young universe, called density fluctuations. There are a few ways these fluctuations might have formed. One idea involves something called axion inflation. In this theory, a mysterious particle called an axion acts like a strange kind of field during inflation, creating ripples and waves in space. These waves could have become the seeds for black holes. Another possibility is reheating, a short moment that came right after inflation ended. During this time, the inflaton field, the energy field thought to have driven inflation, broke down into normal particles. As these particles tried to settle into a balanced state, the process may have been messy, leaving behind clumps of matter heavy enough to collapse into black holes. A third explanation comes from cosmic phase changes. These were times when the universe changed its state, similar to how water turns into ice. Such shifts could have made dense areas or released powerful particles, both of which might have collapsed under their own gravity and become black holes. Now let's go back to one of the biggest and strangest mysteries in modern science, the mystery of dark matter. This puzzle was first suggested way back in the year 1933 by a Swiss-American astronomer named Fritz Zwicky. He noticed something odd when he studied groups of galaxies. They were moving as if there was a lot more matter pulling on them than what we could actually see. Scientists later realized that this wasn't just happening in a few galaxies, it was happening everywhere. It was as if some kind of invisible material was out there, adding extra gravity to the universe. This mysterious stuff became known as dark matter. Even though no one has ever seen dark matter directly, scientists are almost sure it must exist because galaxies and galaxy clusters don't act the way they do without it. But what could dark matter be made of? One fascinating idea is that primordial black holes, often called PBHs, might be the answer. Primordial black holes are very different from the black holes we usually hear about. Normal black holes are formed when giant stars collapse at the end of their lives, but primordial black holes might have formed during the very first moments after the Big Bang, when the universe was still extremely hot, dense, and chaotic. These PBHs might help explain dark matter in three exciting ways. First, if there are enough of them floating around, they could actually make up all or most of the dark matter in the universe. Second, unlike other dark matter candidates like WIMPs, which stands for weakly interacting massive particles, PBHs can create gravitational waves, which are ripples in space and time. These waves can be detected with advanced instruments like LIGO and Virgo, giving us a way to actually listen to the presence of black holes. Third, PBHs might explain some strange cases of gravitational lensing, which is when the light from faraway stars or galaxies bends and twists because of invisible objects in its path. Sometimes this bending doesn't match what we'd expect from ordinary matter. PBHs might be the hidden cause. Even though scientists haven't yet confirmed that PBHs are the true form of dark matter, the evidence is growing. Experts like Bernard Carr and his colleagues have been studying this idea for years, hoping that the key to dark matter lies in the very birth of the universe. What makes PBHs even more interesting is that they don't have to be tiny. They could come in many different sizes, from much smaller than a grain of sand to as heavy as a mountain or even bigger. Because of this, some scientists think PBHs might have helped form the very first galaxies, maybe even before the first stars had a chance to shine. Now let's go back to another space mystery. This one introduced in the year 1974 by a brilliant Soviet scientist named Yakov Zeldovich. He came up with a puzzling idea in space science called the cosmological domain wall problem. He suggested that during the early universe's fast changes called phase transitions, strange, invisible boundaries called domain walls might have formed. These walls would have been full of energy, and if too many of them were created, they could have completely messed up the way the universe developed. But here's the clever part. PBHs might actually fix this problem. Here are three ways PBHs could help with the domain wall problem. 1. If PBHs formed very early, their strong gravity could have pulled matter toward them and caused it to clump together. This clumping might have stopped the domain walls from forming in the first place. 2. If the domain walls had already appeared, PBHs might have helped destroy them. Their gravity could have caused the walls to collapse, maybe even turning into more PBHs. 3. PBHs might simply exist in the universe without causing any trouble. For example, if we found PBHs with weights between 10 to the power of 12 kilograms and 10 to the power of 13 kilograms, that could be just the right amount to explain all the dark matter in the universe, without causing any problems or breaking the rules of physics as we know them. But that's not the end of Zeldovich's brilliant ideas. In the late 1970s, he also suggested something called the cosmological monopole problem. This problem is about magnetic monopoles, which are strange theoretical particles that have only one magnetic pole, either north or south. Normal magnets always have both. According to some theories, monopoles should have formed in the early universe, but no one has ever seen one. Again, PBHs might give an answer. One idea is that if these magnetic monopoles ever existed, they may have been pulled into PBHs by their gravity and swallowed. Another idea is that PBHs could have spread matter out in the early universe, moving the monopoles so far apart that they are almost impossible to find today. Now, let's add a twist from one of the most complex and fascinating theories in physics, string theory. According to general relativity, the tiniest PBH should have completely disappeared by now, slowly evaporating over time because of something called Hawking radiation, a process first suggested by Stephen Hawking in the year 1974. But string theory suggests something surprising. There might be an extra hidden space dimension beyond the three we already know. If that's true, gravity might act differently on small scales. This could slow down the evaporation of tiny PBHs, letting them survive much longer than expected. In simple terms, this hidden dimension could add extra energy that helps small PBHs avoid disappearing. If this idea is correct, there could be thousands of tiny PBHs quietly floating around inside our own Milky Way galaxy. To test this idea, scientists have used a powerful space telescope called the Fermi Gamma Ray Space Telescope, which was launched by NASA on June 11, 2008. If this telescope detects certain patterns in gamma-ray bursts, like tiny flickers or ripples in the energy, it could be the first real sign that PBHs and the extra dimensions predicted by string theory are real. Scientists have also tried to figure out how many PBHs might exist and how heavy they could be. One way to study this is through Hawking radiation. According to Hawking, all black holes slowly lose weight over time by giving off tiny amounts of energy. The smaller the black hole, the faster it disappears. When it gets very small, it could end its life with a sudden, powerful explosion, like a massive hydrogen bomb releasing millions of megatons of energy instantly. For comparison, a normal black hole with a weight about 3 times that of our Sun would take about 10 to the power of 69 years to completely disappear. That is such a huge amount of time it makes the current age of the universe, about 13.8 billion years, look like a blink of an eye. But PBHs could be much smaller. A PBH with a weight around 10 to the power of 11 kilograms would have a lifetime close to the current age of the universe. If many of these PBHs formed during the Big Bang, we might even be able to see some of them finishing their lives and exploding right now, somewhere in our galaxy. In the month of June in the year 2008, NASA launched a powerful space telescope called the Fermi Gamma Ray Space Telescope. One of its main jobs was to search for strange and powerful events in the universe, including signals that might come from primordial black holes, tiny black holes that may have formed right after the Big Bang. Based on what Fermi has seen over the years, scientists now think that if primordial black holes exist, they cannot make up more than 1% of all dark matter, at least not the ones that weigh up to 10 trillion kilograms, 10 to the power of 13 kilograms. There's another clue. If there had been a lot of these tiny black holes in the early universe, their energy would have affected how the first light elements like hydrogen and helium were made. The balance of these elements is very exact, and anything that disturbed it would leave a clear mark in the universe. But here comes a tricky part. A famous scientist named Stephen Hawking once suggested that black holes should slowly lose weight by giving off radiation, now called Hawking radiation. If this radiation really exists, then tiny black holes could eventually disappear. But if Hawking radiation is just an idea and not real, then these small black holes would be almost impossible to find. They are so tiny and have so little gravity that they wouldn't pull in much matter or give off much energy, making them almost invisible. Back in the earliest moments of the universe, just after the Big Bang, some scientists think that very tiny black holes might have formed from collapsed clumps of energy and matter. These are called primordial black holes, or PBHs for short. If they did exist, they could have pulled in matter around them, heating it up and releasing energy into space. This energy would have had a big effect during a key moment in the universe's early history, an event called recombination, when the universe cooled enough for atoms to form and light started to travel freely through space. This ancient light, known as the cosmic microwave background, or CMB, still fills the universe today. It carries tiny temperature differences called anisotropies, which scientists can measure with amazing accuracy. A space telescope called Planck, which studied the CMB in great detail, showed that if primordial black holes were as heavy as between 100 and 100,000 times the mass of our Sun, they probably couldn't make up a large part of dark matter, at least according to the simplest ideas we have. But some scientists think this might change if we use more complex models of how the universe works. There's another interesting idea. Maybe dark matter, the invisible stuff that makes up most of the matter in the universe, is made of special particles called WIMPs, which stands for weakly interacting massive particles. If these WIMPs gathered around a primordial black hole in a kind of cloud, they could bump into each other and destroy each other in a process called annihilation. This would release powerful light in the form of gamma rays, which space telescopes like Fermi are made to detect. Now, in the years ahead, scientists will use many advanced tools and experiments to keep searching for signs of these mysterious black holes. The Square Kilometre Array, SKA. This huge radio telescope will study how primordial black holes may have changed the time when the first stars and galaxies started to shine. If black holes released energy by pulling in gas, they could have changed how the universe became reionized when light returned after a period of cosmic darkness. Gravitational wave detectors, LIGO and Virgo. These detectors have already found black holes crashing into each other. If they detect black holes smaller than 1.4 times the Sun's mass, it would be unusual, since normal black holes from dying stars are usually bigger. Finding smaller ones might be a strong hint that they are primordial. These detectors can also see if the black holes are moving in strange stretched-out orbits, which would be another possible clue. LISA and pulsar timing arrays. LISA, short for Laser Interferometer Space Antenna, and other tools like pulsar timing arrays are being made to detect very faint ripples in space and time caused by primordial black holes orbiting each other before they crash together. Tiny dwarf galaxies and their star clusters. Some small galaxies are filled with dark matter. If primordial black holes are hiding there, studying the stars in their centers might show something. If a primordial black hole is nearby, it could slightly change the motion of stars around it. By carefully watching star movements, scientists might find signs of one. Some researchers have even suggested that if a tiny black hole passed through Earth, it would make a special kind of sound-like signal. Since these black holes are small but very heavy and extremely fast, they could zip through the planet with only a few tiny effects, without causing any damage. If a primordial black hole ever passed through a star, its strong gravity might make the star ripple or shake. These tiny vibrations might be seen by astronomers. When a black hole passes in front of a faraway star or a bright object like a quasar, its gravity can bend the light. Scientists can look for this strange bending of light, called microlensing, to find hidden black holes. If a tiny but fast-moving primordial black hole passed through the solar system, it might tug slightly on a planet like Mars. This tug could be seen as a small, sudden change in its orbit. Even though none of these tools were made just to find primordial black holes, each one can give useful clues. Together, they make a powerful set of tools for solving the mystery. Cosmic Explorer and Einstein Telescope. These are future versions of LIGO and Virgo that will be even more sensitive. They will be able to detect gravitational waves from farther back in time, possibly spotting the faint signals left by primordial black holes. Nanograv. This project recently picked up a strange signal. If it turns out to be from gravitational waves caused by black holes smaller than the Sun, it might be the first strong evidence for primordial black holes. LISA will also be able to detect a special kind of event where a small black hole spirals into a much bigger one. This could give more ways to find primordial black holes and confirm signals like the one Nanograv saw. The Atomic Experiment for Dark Matter and Gravity Exploration in Space is a planned mission that hopes to catch signals from medium-sized black holes crashing into one another. If it works, this experiment could provide important evidence that primordial black holes, those formed in the earliest moments of the universe, played a role in creating the enormous supermassive black holes we now see at the centers of giant galaxies. Imagine uncovering a cosmic clue that links the very beginning of time to the massive structures we observe today. The Nancy Grace Roman Space Telescope will use a clever method called astrometric lensing. This is when the position of a star appears to shift just a little bit as a dark object passes in front of it. By watching these tiny wobbles in the sky, astronomers hope to spot black holes that would otherwise remain invisible. The Vera C. Rubin Observatory, also known as the Large Synoptic Survey Telescope, is a ground-based telescope designed to look for very brief flashes of light caused by microlensing. These tiny flashes can reveal the masses of hidden objects, including black holes. It might even detect rare cosmic fireworks called kilonovae, which could be connected to primordial black holes, tiny signals that carry huge secrets about the universe's earliest days. The Next Generation, Very Large Array, or NVLA, is a cutting-edge radio telescope that will complement other projects such as Nanograv, which studies gravitational waves. By working together, these tools could help confirm whether certain gravitational wave signals actually come from collisions between primordial black holes. Another exciting clue comes from fast radio bursts, or FRBs. These are sudden, extremely powerful flashes of radio waves coming from far across the universe. If a primordial black hole happens to pass between Earth and one of these bursts, it could bend the signal in a detectable way. By observing many FRBs, scientists might start to notice patterns that point directly to these ancient black holes. There is also a mysterious part of the universe's gamma-ray spectrum called the mega-electron-volt (MeV) band that has barely been explored. If new detectors are built to study this range, scientists could place tighter limits on how many primordial black holes exist, especially those with masses similar to large asteroids. For instance, a primordial black hole with a mass around 5 × 10 to the power of 19 grams, roughly the mass of a very large asteroid, would slowly evaporate, releasing extremely high-energy tera-electron-volt gamma rays. These rays would appear as random bursts scattered across the sky. Special wide-field telescopes, designed to capture sudden bright events, could detect these bursts even if they are observing only small patches of the sky at a time. It's important to remember that not all black holes are the same. Some are born much later, forming from the collapse of huge clouds of gas long after the Big Bang. Primordial black holes are unique. They may have formed in the first tiny fraction of a second after the Big Bang, collapsing directly from waves of energy in the newborn universe. As scientists continue to build better instruments and observe the skies with greater precision, they may finally uncover the truth about these mysterious ancient black holes. In doing so, they could unlock secrets that have been hidden for billions of years, offering a glimpse into the very birth of the universe itself. A rotating black hole is a truly fascinating kind of cosmic object. Unlike a regular black hole that just sits there quietly, a rotating black hole spins around one of its own axes, much like a twirling top or a spinning figure skater. This spinning motion means the black hole has something called angular momentum, which is just a fancy way of measuring how fast and in what manner an object rotates. Almost everything we know in the universe spins in some way. Planets like our Earth rotate around their axes, stars like our Sun spin on their own centres, entire galaxies slowly whirl in space, and even black holes can spin. So it makes perfect sense that most black holes, which are born either when massive stars collapse under their own gravity, or when huge cosmic objects collide, end up spinning as well. Physicists studying gravity through Einstein's famous theory of general relativity have worked out exact mathematical descriptions of black holes. There are 4 key solutions in total, and 2 of these describe spinning black holes. These are called the Kerr black hole and the Kerr-Newman black hole. According to an important idea known as the no-hair theorem, once a black hole has settled down and become stable, it can be fully described by just a few simple properties: its mass, how fast it spins, and its electric charge. These properties can be measured from far away by observing the black hole's gravitational pull and any electromagnetic effects it produces. Everything else, like the exact way the black hole formed, or the details of the matter that once fell in, is lost forever inside, or stretches off to infinity. This is because nothing happening inside the black hole's event horizon, the invisible boundary around it, can affect anything outside. Here's another interesting point. When stars collapse to form black holes, they're almost always already spinning. That means most black holes formed in nature should also spin. Stars and other cosmic objects usually do not carry a strong electric charge, so any charge a black hole might have is quickly neutralized by attracting opposite charges. For this reason, most real black holes are thought to be electrically neutral, but they still spin. When scientists talk about the black holes we actually find in space, they usually mean Kerr black holes, spinning, but with little or no electric charge. Rotating black holes can be created in several ways. The most common is when a massive spinning star collapses under its own gravity. Another way is when groups of compact objects such as stars, gas clouds, or the remnants of dead stars collide or fall together, carrying some overall spin. In fact, because all stars naturally rotate and collisions rarely occur without some twisting motion, many astronomers believe that all black holes in the universe are, in some way, spinning. In late 2006, astronomers published an exciting study in the Astrophysical Journal. They measured the spin rate of a black hole called GRS 1915 + 105, located in our Milky Way galaxy. Their findings suggested that this black hole could be spinning as fast as 1,150 times every single second. To put that into perspective, that's astonishingly close to the maximum spin a black hole can possibly achieve. Scientists also believe that when a rotating star collapses into a black hole, it can unleash an extremely powerful burst of gamma rays, called a gamma ray burst. These bursts are so strong that they can travel across the vast distances of the universe and be detected by special telescopes right here on Earth. Now here comes something truly mind-blowing. Rotating black holes can actually release energy. They can convert some of their rotational energy into other forms of energy, and one way this can happen is through a process called the Penrose process. This occurs in a strange region around the black hole known as the ergosphere. This is a zone just outside the event horizon, where space itself is being dragged and twisted around by the black hole's intense spin. Over long periods of time, if energy keeps being extracted from the black hole in this way, its spin could gradually slow down, eventually turning it into a Schwarzschild black hole, a black hole that does not spin at all. In practice, however, most scientists believe that the spin of a black hole never actually drops all the way to zero, meaning these cosmic whirlers keep some of their incredible rotational energy almost forever. Rotating black holes are some of the most fascinating objects in the universe, and scientists have studied them using special mathematical solutions known as the Kerr and Kerr-Newman metrics. These solutions are based on the famous equations Albert Einstein came up with in the year 1915, called his field equations. Thanks to these solutions, physicists have a powerful way to understand how spinning black holes behave, especially in the regions just outside their event horizons, the invisible boundaries beyond which nothing, not even light, can escape. Around a black hole, space itself is stretched, twisted and bent in ways that seem almost magical. Light travelling near a black hole doesn't move in straight lines. Instead, it can curve dramatically, sometimes looping around the black hole multiple times before it finally escapes. This strange behaviour means that if you were observing a distant galaxy that lies behind a black hole, you might not see just one image of that galaxy. Instead, you could see multiple warped and twisted versions of it, all created by the black hole's immense gravity bending the light. In the year 2021, scientists published a complete mathematical explanation of exactly how light bends as it moves around the spinning middle, or equator, of a Kerr black hole. The story of rotating black holes goes even further back. In the year 1963, a mathematician named Roy Kerr discovered a special solution describing a spinning black hole. But for decades, scientists weren't completely sure whether this solution was stable. That is, whether real black holes could actually exist in this form without quickly falling apart. Then, in the year 2022, mathematicians proved that Kerr's solution is indeed stable. This remarkable result confirmed that the spinning black holes predicted by Einstein's equations over 100 years ago could truly exist, lasting over long stretches of cosmic time. Rotating black holes are not only strange in how they bend space and light, they also have surprising thermal behaviours. They can exist in two temperature states, heating up or cooling down. When a rotating black hole gives off energy, it loses some of its spin and becomes hotter. When it stops releasing energy, it slowly cools down. These changing temperature states add yet another layer of mystery to these cosmic giants, making them even more fascinating and complex than we could have imagined. A binary black hole, often called a black hole binary, is like a cosmic pair dancing a mysterious invisible waltz in the depths of space. Picture two enormous invisible giants locked in a gravitational embrace, circling each other with relentless intensity, yet hidden in the profound darkness of the universe. These extraordinary pairs come in two main varieties. The first type is called binary stellar mass black holes. These form when two enormous stars, far heavier than our Sun, grow old and die together. As these stars reach the end of their lives, they explode as supernovae and collapse under their own gravity, turning into black holes. If these stars were orbiting each other before, their black hole remnants may continue to orbit in the same cosmic dance. Occasionally, two black holes that were not born together might drift close enough in space to become a gravitationally bound pair, forming a binary system from strangers. The second type is far larger and far more mysterious: binary supermassive black holes. These form during the collision of two entire galaxies. Each galaxy typically hosts a gigantic black hole at its centre, and when galaxies merge, these central black holes slowly inch toward one another over millions of years. Eventually, they may start orbiting each other, creating a super heavyweight version of the stellar mass binaries, moving at scales almost unimaginable. For many decades, scientists could only guess about these pairs and rely on indirect clues. Black holes are notoriously difficult to detect because they emit no light, appearing as cosmic phantoms, invisible, yet immensely powerful. The tools available in the 20th century were not sensitive enough to observe them directly, A major clue came from a spectacular phenomenon. When two black holes collide, they release enormous bursts of energy, not as light or sound, but as gravitational waves. These are tiny ripples that stretch and squeeze the very fabric of space-time, much like the ripples formed when a stone drops into a pond. Albert Einstein predicted these ripples over 100 years ago in his general theory of relativity, even describing the unique patterns or waveforms that such events would produce. By the late 20th century and the early 21st century, scientists were eager to find concrete evidence. They realized that the clearest proof of gravitational waves would come from detecting the spiraling merger of a pair of black holes. Such an event would produce one of the most powerful gravitational signals in the universe. As two black holes orbit each other, they emit gravitational waves, slowly losing energy. This loss causes the pair to spiral inward, moving faster and faster in a stage known as the inspiral. Eventually they collide in a violent merger, forming a single, larger black hole. After the merger, the new black hole undergoes a stage called the ring-down, as it settles into a smooth, stable shape while emitting the final gravitational waves from the leftover energy. In the moments before the merger, the black holes reach astonishing speeds, and the energy released in gravitational waves peaks during that final fraction of a second. On the 14th of September in the year 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected an incredible signal. This signal was named GW150914. What LIGO had captured was essentially the sound of two black holes merging over 1,300,000,000 light-years away. Each of these black holes weighed roughly 30 times the mass of our Sun, and when they collided, the energy released in gravitational waves was equivalent to about 3 solar masses. At its peak, the energy burst reached approximately 3.6 times 10 to the power of 49 watts. More energy than all the stars in the visible universe combined at that instant. The official announcement came in February of the year 2016, marking the first undeniable proof that binary black holes and gravitational waves truly exist. Since then, many more mergers of stellar mass black holes have been observed, but finding clear evidence of supermassive black hole binaries has proven far more challenging. Some galaxies, such as NGC 6240, show two bright centers that may hint at supermassive black holes slowly approaching each other. Others, like SDSS J104807.74 plus 005543.5 and EGSD 2J142033.66525917.5, emit strange light patterns that could signal two supermassive black holes orbiting closely. In certain galaxies, the central light pulses in a rhythmic pattern, almost like a beating heart. This may be caused by one supermassive black hole circling another, with the galaxy OJ287 being a famous example. Then there's galaxy J 0437 plus 2456, where a supermassive black hole seems to move oddly. Some scientists suggest it may be pushed by another nearby black hole, or even recoiling after a recent collision. A fascinating quasar, PKS 1302-102, may host two supermassive black holes orbiting each other in a cycle lasting about 1,900 days. When galaxies merge, their central black holes often do not collide immediately. Instead, they swing past each other in wide loops, like dancers narrowly missing each other's arms. To finally come together, they need to lose energy. This is helped by a process called dynamical friction. As a black hole moves through a galaxy full of stars, its gravity tugs on them, stealing energy and slowing down the black hole. Eventually, black holes may approach within a few parsecs of each other, but here's the tricky part. Once they get that close, they have already cleared out most nearby stars and gas. Without anything left to slow them down, their orbit can stall, potentially for longer than the current age of the universe. This is known as the final parsec problem, understanding how black holes close that last cosmic gap. Thankfully, when black holes reach extremely small separations, just a few thousandths of a parsec, gravitational waves dominate. They efficiently remove energy, sending the black holes on a direct path toward a dramatic merger. To help black holes traverse the final parsec, scientists have proposed clever solutions. Extra matter, like stars or gas clouds, can tug on the black holes, helping them lose energy. Some researchers even consider special forms of dark matter, which could interact in just the right way to assist in the process. In rarer scenarios, a third supermassive black hole may enter the scene, perhaps due to a second galaxy collision. The three black holes can interact chaotically, bouncing off each other and losing energy more efficiently. These interactions stretch their orbits and amplify the gravitational waves each time they pass closely. To understand the complex dance of black holes, scientists rely on advanced mathematics and supercomputers. In early stages, post-Newtonian approximations are used, like building Newton's laws with extra layers from Einstein's relativity. The effective one-body method simplifies the problem by turning a two-body system into a one-body problem, especially useful when one black hole is much larger than the other. During the ring-down phase, perturbation theory calculates how the new black hole vibrates. The result is typically a spinning Kerr black hole, whose vibrations create distinctive gravitational wave patterns. To simulate the entire process, from in spiral to ring-down, scientists use numerical relativity, a computational approach that models the swirling dance of space and time as black holes spiral, collide, and merge.